Hello there and welcome to Science for Sleep, a quiet place where we take large scientific questions, slow them down, and examine them without any need to hurry. Tonight we are looking far beyond the familiar stars, beyond the bright nearby galaxies, and back toward a period when the universe was still very young. Our subject is a surprising detection made with the Atacama Large Millimeter / submillimeter array, better known as ALMA. Astronomers use this remarkable observatory to detect oxygen in a galaxy so distant that we see it as it existed less than 300 million years after the Big Bang. That is much earlier than many scientists expected to find a galaxy with such clear signs of chemical development. The object has the tidy name JADES-GS-Z14-O, which sounds less like a galaxy and more like a password created by someone who had run out of patience. Yet behind that technical label is one of the most important early galaxies astronomers have studied. Its light has travelled for roughly 13.4 billion years before reaching our instruments. The signal arriving today began its journey when the universe was only about 2% of its current age. Before we settle into the details, take a moment to notice where you're listening from. Perhaps it is late evening. Perhaps the room is dark apart from the screen beside you. Maybe it is early morning, and sleep has not arrived as easily as you hoped. What time is it where you are, and how far do you imagine the oldest light in the universe has travelled before reaching your little corner of Earth? There is no need to calculate it. Astronomers have already taken care of enough calculations for all of us tonight. If you enjoy these calm journeys through science, you can leave a like and subscribe to the channel. It helps other curious listeners find this quiet space, and it lets us continue exploring subjects that are interesting enough to think about, but gentle enough, hopefully, to fall asleep to. You can also share where you are listening from. It is always pleasant to imagine people in different places looking up at the same universe, even if some of them have better weather for it than others. The discovery we're beginning with sounds simple when reduced to one sentence. ALMA found oxygen in an extremely distant galaxy, but that sentence needs careful unpacking, because nearly every word in it carries more meaning than it first appears to. ALMA did not collect a container of oxygen from deep space. No one opened a hatch in the Atacama Desert and found a small delivery from the early universe. The oxygen was identified through light, or more precisely, through a specific form of electromagnetic radiation emitted by ionized oxygen atoms inside the distant galaxy. It is also important to be clear about what kind of oxygen was found. This was not evidence of breathable oxygen gas, oceans, forests, animals, or life. It was a detection of oxygen atoms in ionized gas, revealed by a characteristic emission line. In ordinary conversation, oxygen usually means the gas we breathe. In astronomy, the word often refers more broadly to the element itself, wherever it appears and whatever form it takes. That distinction matters because the real surprise was not biological. It was chemical and historical. Oxygen is not one of the elements that the universe began with in large quantities. In the earliest period after the Big Bang, the cosmos was made mainly of hydrogen and helium, with a very small amount of lithium. Heavier elements had not yet been manufactured in significant amounts. They had to be built later inside stars. The oxygen in your body, the oxygen in rocks, the oxygen in water, and the oxygen detected in this remote galaxy all owe their existence to earlier generations of stars. Inside massive stars, intense heat and pressure allow atomic nuclei to combine through nuclear fusion. Over time, these reactions produce heavier elements. Oxygen is one of the important products. When massive stars reach the end of their lives, they can release those elements into surrounding space, particularly through powerful stellar winds and supernova explosions. The enriched material can then mix with gas, become part of later stars, and contribute to planets and other structures. Chemical enrichment therefore takes time. Stars must form, live, produce heavier elements, and return some of those elements to their surroundings. That sequence is the reason the ALMA result caused such interest. JADES-GS-Z14-. existed at a time when the universe had not been around for very long. Astronomers expected the first galaxies to be chemically simple, dominated by hydrogen and helium, with only small quantities of heavier elements. Finding a strong oxygen signal suggested that this galaxy had already gone through substantial star formation and enrichment. The process appeared to have happened quickly, perhaps much more quickly than standard expectations had allowed. 2 independent research teams examined ALMA observations and reported the oxygen detection. The signal came from a far-infrared emission line produced by doubly ionized oxygen, usually spoken as oxygen-3 and written with the astronomical notation O3. In the galaxy's own rest frame, the line has a wavelength of about 88 micrometers. Because the universe expanded during the long journey of the light, that wavelength was stretched into the millimeter range by the time it reached Earth. ALMA is designed to observe precisely this kind of radiation. The amount of stretching is described by redshift. For this galaxy, the oxygen line gave a redshift of about 14.18. A redshift that large is difficult to picture because it is far beyond anything encountered in ordinary life. It does not simply mean that the galaxy is moving away in the same way that a car moves down a road. It reflects the expansion of space itself during the billions of years the signal was travelling. The greater the expansion, the more the wavelength is stretched toward the red end of the spectrum and beyond into infrared and millimeter wavelengths. The galaxy had already been identified with the James Webb Space Telescope. Webb is exceptionally capable of detecting faint infrared light from very distant galaxies. Its observations indicated that JADES-GS-Z14-0 was extraordinarily remote. ALMA then provided a precise measurement of the oxygen emission line, greatly tightening the distance estimate. The 2 observatories were doing different but complementary jobs. Webb found and studied the galaxy through infrared observations, while ALMA examined longer wavelengths and identified a line that could pin down the redshift with unusual accuracy. When the ALMA findings were publicly announced in March 2025, JADES-GS-Z14-0 was the most distant spectroscopically confirmed galaxy known. Astronomy continued moving, as it tends to do, and another object later took that particular record. The importance of the oxygen detection did not depend entirely on the galaxy keeping first place forever. Records are useful for headlines, but the lasting scientific value comes from the information contained in the observation. This galaxy still provides a remarkably early view of chemical enrichment, only a few 100 million years after the universe began. This partnership between Webb and ALMA matters because early galaxies are difficult to study. They are faint, small, and very far away. Their light has been stretched by cosmic expansion. Some wavelengths are absorbed or altered before reaching us. Even when a telescope detects a distant object, astronomers must work carefully to establish what it is, how far away it lies, and which physical processes are producing the signal. A bright spot in an image can raise a question, but spectroscopy often provides the stronger evidence needed to answer it. Spectroscopy means separating light according to wavelength. You can think of it as taking a mixed signal and spreading it out so that individual features become visible. Different atoms and ions interact with light at specific wavelengths. They leave recognizable lines in a spectrum rather like identification marks. When astronomers find the expected line at a shifted wavelength, they can identify the element and calculate the redshift. It is less dramatic than catching a glowing oxygen atom in a net, but it is far more practical. In this case, ALMA detected the 88 micrometer line from doubly ionized oxygen. Doubly ionized means that the oxygen atoms had lost 2 electrons. This tends to occur in regions exposed to energetic radiation from young, massive stars. The line therefore tells astronomers more than the simple fact that oxygen existed. It also provides information about the ionized gas and the active star-forming environment inside the galaxy. A single spectral feature can act as a distance marker, a chemical clue, and a sign of energetic stellar activity all at once. Astronomers are very fond of efficient clues. The result attracted attention because the oxygen line was detected clearly, not merely suggested by a vague bump that might disappear after another cup of coffee and a revised calibration. One study reported a detection significance of 6.6 sigma. In scientific terms, that indicates a very low probability that the signal arose from random noise. The exact analysis and interpretation still require care, as they always do, but the line itself was not treated as a casual possibility. Measurements associated with the galaxy suggested a level of chemical enrichment somewhere around 5 to 20% of the Sun's metallicity in one analysis. Astronomers use the word metallicity in a way that can confuse anyone who has not spent much time around astronomers. In this context, a metal is essentially any element heavier than helium. Oxygen counts as a metal, even though no one would recommend making a saucepan from it. Metallicity is therefore a measure of how much heavier element material is present compared with hydrogen and helium. The announcement described JADES-GS-Z14-0 as having roughly 10 times more heavy elements than expected for such an early galaxy. That does not mean it contained more heavy elements than the Milky Way or the Sun. It means that, given how soon it appeared after the Big Bang, its chemical development was surprisingly advanced. The important comparison is with theoretical expectations for that period, not with the mature universe around us today. To understand the timing, imagine compressing the current age of the universe into a single calendar year. In that comparison, 300 million years would occupy only the first several days of January. JADES-GS-Z14-0 would appear very near the beginning, long before the cosmic year had properly settled into its routine. Yet the galaxy had already formed stars, produced oxygen, and distributed at least some of that oxygen into ionized gas. It had completed several steps that require physical processes to occur in sequence. That does not necessarily mean every existing theory has failed. Scientific models include ranges, assumptions, and uncertain details. Early galaxy formation is an active field, and observations from Webb have already shown that some galaxies in the young universe were brighter, more massive, or more developed than earlier surveys led researchers to expect. The ALMA oxygen result adds another strong piece of evidence. Galaxies may have begun forming stars sooner, formed them more efficiently, or cycled material through massive stars more rapidly than many models predicted. Several possibilities can contribute to rapid enrichment. The first stars in a galaxy may have been massive and short-lived. A very massive star can complete its life in only a few million years, which is brief on a cosmic scale. Repeated generations of such stars could enrich the gas quickly. Star formation might also have been intense, producing many massive stars within a relatively compact region. Gas flows, supernova feedback, and the distribution of matter inside the early galaxy would all influence how fast oxygen spread and where the emission line formed. There is still much to learn about the object. Astronomers want to know how much stellar mass it contains, how rapidly it was forming stars, how its gas moved, how much dust was present, and whether its unusual brightness reflects a brief burst of activity or a more sustained period of growth. They also want to know whether JADES-GS-Z14-0 is rare, or whether it belongs to a wider population of unexpectedly mature early galaxies that current instruments are only beginning to reveal. A single galaxy can be informative, but it cannot define the whole early universe. Perhaps JADES-GS-Z14-0 formed in an especially dense region. Perhaps it had access to abundant gas. Perhaps its stellar population produced oxygen unusually efficiently. It may be exceptional. On the other hand, it may be an early clear example of something common that previous telescopes simply could not detect. Astronomy often changes in this way. A new instrument finds one surprising object, then another, and eventually the surprise becomes a category. This is why the wording "earlier than scientists expected" deserves a little care. Science does not operate with one fixed expectation shared by every researcher. Different simulations and theoretical models can produce different outcomes. Some allow rapid early enrichment more readily than others. The discovery does not tell us that scientists believed oxygen could not exist at all by this time. Massive stars can produce oxygen quickly. The larger surprise is the apparent amount of enrichment and the maturity implied by the observations within such a short cosmic interval. There is also a useful distinction between the first oxygen ever created and the earliest oxygen we have detected directly. The ALMA observation does not prove that this was the first oxygen in existence. Oxygen must have formed in stars before the light we see from this galaxy was emitted. The record announced in 2025 concerned observation. It was the most distant detection of oxygen then reported, allowing astronomers to study the element at an earlier known stage of cosmic history than before. When headlines say that ALMA found oxygen, they compress a long process into 2 words. The observatory collected millimeter and submillimeter radiation, using many antennas working together. The data were calibrated, combined, and analysed. Researchers searched for spectral features within a predicted frequency range. They compared results, estimated uncertainties, and tested whether the signal was real. Separate teams reached compatible conclusions. Only after all of that could the finding be presented in a form that fits neatly into a headline. The location of ALMA is central to what it can do. Its antennas stand high on the Chinantor Plateau in northern Chile, where the air is extremely dry. Water vapor in Earth's atmosphere absorbs much of the millimeter and submillimeter radiation astronomers want to observe. A high, dry site reduces that interference. The environment is difficult for people, equipment, and any unattended cup of tea, but it gives the antennas a clearer view of wavelengths that would be much harder to measure from lower and wetter locations. ALMA is not a single dish. It is an array of antennas that can be coordinated so that they behave like parts of a much larger telescope. This method is called interferometry. By comparing the signals received at different antennas, astronomers can achieve much finer detail than a lone antenna of similar size could provide. The antennas can also be moved into different arrangements, changing the effective scale of the array and allowing it to examine different kinds of structures. Nothing about this process resembles ordinary vision. ALMA does not take a simple colour photograph through an eyepiece. Its receivers measure faint radio frequency signals. Computers combine the observations. Astronomers reconstruct images and spectra from the data. The final result may be displayed as a graph, a map, or a coloured image, but the colours are often chosen to represent intensity or wavelength, rather than what a human eye would see. This is one reason astronomy requires both instruments and interpretation. The universe sends information in many forms, and our eyes detect only a small fraction of them. The oxygen line from JADES-GS-Z14-0 began at a much shorter wavelength than the one ALMA received. Cosmic expansion stretched it by a factor of more than 15. A line emitted at 88 micrometers arrived at roughly 1.3 millimeters. That shift placed it within ALMA's observing range. In a sense, the expansion of the universe moved the signal into the instrument's area of expertise. This was helpful, although waiting more than 13 billion years for the wavelength adjustment is not a method most laboratory technicians would recommend. The great distance also means that observing the galaxy is a form of looking into the past. We do not see JADES-GS-Z14-0 as it is now. We see it as it was when the light left. The galaxy may have changed beyond recognition, merged with other systems, or become part of a much larger structure during the billions of years since then. There is no way to receive a current photograph because any newer light is still travelling toward us. Astronomy always comes with delayed information. For nearby objects, the delay is small. For this galaxy, it covers almost the entire history of the universe. That delay is not a flaw. It is what makes distant galaxies valuable. Different distances allow astronomers to observe different periods of cosmic history. Nearby galaxies show relatively recent conditions. More remote galaxies reveal earlier stages. By comparing many objects across many distances, researchers can build a sequence of how galaxies formed and changed. JADES-GS-Z14-O provides a view unusually close to the beginning of that sequence. The presence of oxygen changes what researchers infer about the pace of the sequence. Before oxygen could appear in the surrounding gas, stars had to form from more primitive material. Some of those stars had to produce oxygen. At least some had to release it. The enriched gas then had to become ionized strongly enough to emit the detected line. All of this occurred while the universe was still under 300 million years old. The timetable is tight, and the galaxy appears to have used it efficiently. There is a human tendency to assume that early means simple. We imagine the beginning of anything as slow, incomplete, and tentative. Sometimes that is reasonable. A new city begins with a few roads. A new forest begins with scattered growth. A new scientific project begins with a folder named Final, followed eventually by several folders named Final Revised 2, and Final Actual. The early universe, however, didn't necessarily proceed at a comfortable administrative pace. Gravity, gas, radiation, and nuclear physics were already operating. Once conditions allowed structures to form, some regions may have developed rapidly. This galaxy therefore invites a better question than simply asking why oxygen existed so early. The deeper question is what sequence of events allowed so much chemical enrichment to happen so quickly. Answering that will require closer attention to the first stars, the rate of star formation, the movement of gas, and the way early galaxies assembled. It will also require more observations of other galaxies from the same period. One surprising object is a clue. A collection of them can become a pattern. Tonight, we will take that process slowly. We will look at the observatory that received the signal, the conditions of the young universe, the galaxy itself, the spectral line that revealed the oxygen, and the stellar processes that made the element possible. We will also examine why the result challenged expectations without exaggerating what it proves. The aim is not to turn a careful measurement into a dramatic claim that solves every mystery. It is to understand why a faint line in a spectrum can force scientists to reconsider how quickly the first galaxies grew. For now, settle into whatever position is most comfortable. Let the scale of the subject remain large without asking your mind to hold every number at once. The key facts are simple enough. A galaxy called JADES-GS-Z14-O was already shining less than 300 million years after the Big Bang. Its light travelled for about 13.4 billion years. The James Webb Space Telescope identified it as an extremely distant galaxy. ALMA detected a line from ionized oxygen and measured its redshift with remarkable precision. Its full name is the Atacama Large Millimeter / submillimeter array. The name describes 3 practical facts. It is located in the Atacama region of northern Chile. It observes millimeter and submillimeter wavelengths, and it is an array, meaning that it does not depend on one large dish. It uses many antennas whose measurements are combined. The antennas stand on the Chananto Plateau, about 5,000 meters above sea level. At that altitude, the air is thin, the weather can be severe, and ordinary physical effort becomes more difficult. The site is not high, because astronomers enjoy making maintenance inconvenient. It is high because the atmosphere between a telescope and space is part of every ground-based observation. For the wavelengths ALMA studies, one atmospheric ingredient causes particular trouble: water vapor. Water molecules absorb portions of millimeter and submillimeter radiation. A humid atmosphere can block or weaken signals before they reach the ground. The Atacama Desert is one of the driest places on Earth, and the high plateau places the antennas above much of the water vapor that remains. The result is not a perfect window because no ground sight removes the atmosphere entirely, but it is an unusually clear one. ALMA can observe frequency ranges that would be difficult or impossible to use reliably from wetter, lower locations. The environment that helps the astronomy creates problems for the people and machines. The antennas must operate through strong winds, large temperature changes, intense sunlight, snow, dust, and low oxygen levels in the air. Their surfaces must keep an extremely accurate shape because small imperfections can distort the incoming radio waves. Each antenna also has to point precisely and move smoothly while carrying sensitive receivers and electronics. A radio antenna may look simple from a distance, rather like an unusually serious satellite dish, but its useful simplicity ends as soon as the engineering details begin. Most staff do not spend an entire working day at the 5,000-meter site. The operation support facility is lower, at roughly 2,900 meters, where assembly, maintenance, control work, and much of the daily human activity can be carried out under less punishing conditions. Equipment that requires major attention can be brought down from the plateau. Even there, the altitude is noticeable. The array's location therefore affects not only how observations are made, but how the observatory is operated as a workplace. ALMA has 66 high-precision antennas. 54 are 12 meters across and 12 are 7 meters across. The 12-meter antennas do not all perform exactly the same role. 50 form the main 12-meter array, while 4 can work as total power antennas. The 12 smaller dishes form part of the Atacama compact array, often called the ACA. These groups can be used together to recover information on structures of different apparent sizes in the sky. The reason for having several groups becomes clearer when we consider what an interferometer measures. A single radio dish collects radiation across its surface and focuses it toward a receiver. A larger dish can normally distinguish finer detail, but building one solid, steerable dish many kilometers across is not a realistic engineering plan. It would also make finding a sufficiently large cupboard for spare parts rather difficult. Interferometry offers another approach. Separate antennas observe the same target at the same time. Their signals are recorded with extremely accurate timing, then compared and combined. The distance and direction between each pair of antennas form what astronomers call a baseline. Every baseline samples information about structure in the source. With many antennas, there are many pairs, and therefore many simultaneous measurements. ALMA's antennas can be placed in different configurations. In compact arrangements, they sit relatively close together. In extended arrangements, some are separated by distances of up to about 16 kilometers. A wider separation can reveal finer detail, while a compact arrangement is better at detecting broader, more extended emission. There is no single arrangement that is best for every target. Astronomers choose a configuration based on the size and detail of the structure they need to measure. This does not mean that the array simply behaves like a perfectly filled dish 16 kilometers wide. Large spaces remain between the antennas. The array samples parts of the available information rather than collecting every possible measurement at once. As Earth rotates, the relative orientation of the baselines changes, allowing the array to sample additional information over time. Astronomers then use mathematical reconstruction to produce an image that is consistent with those measurements. That reconstruction must be handled carefully. Interferometric data do not begin as a familiar photograph. They begin as measurements of how signals from different antennas relate to one another. Software converts those measurements into an image, and the result depends on calibration choices, weighting, resolution, noise, and the coverage provided by the baselines. This is why radio astronomers often inspect the data in several forms instead of admiring one finished picture and going home early. The smaller ACA antennas help fill an important gap. Closely spaced antennas are sensitive to broad emission that can be missed by an array using only longer baselines. The total power antennas add measurements similar to those from individual single dishes. helping recover emission on still larger scales. By combining the main array, the compact array, and total power observations, researchers can study both fine detail and extended structure. A nearby molecular cloud and a tiny distant galaxy place very different demands on an instrument, so flexibility is essential. Every antenna begins the process by collecting electromagnetic radiation. The dish reflects incoming waves toward a secondary system and then to a receiver. ALMA's receivers cover a series of frequency bands across the millimeter and submillimeter range. Different bands are used for different targets and spectral lines. The full receiver system is designed to work across wavelengths from several millimeters down to a fraction of a millimeter, although not every observation uses the whole range. A proposal identifies the frequencies needed for a specific scientific question. The signals are weak, and the receiving system adds its own thermal noise unless it is cooled. ALMA therefore keeps key receiver components at cryogenic temperatures. The cold electronics allow the detectors to measure extremely faint radiation with less interference from the instrument itself. The cooling system is hidden inside each antenna, so nothing about the outside view suggests that part of the telescope is operating only a few degrees above absolute zero. The desert may be cold at night, but it is not quite helpful enough to do the entire job naturally. After the receivers collect the signal, the information is converted, digitized, and transmitted through the observatory's electronics. Precise timing is vital. A wave reaches each antenna at a slightly different moment because the dishes occupy different positions. Those tiny differences contain the spatial information that makes interferometry useful. They must be preserved accurately, not averaged away or confused with delays introduced by cables and equipment. The signals reach a specialized computer system called a correlator. Its task is to compare the data from pairs of antennas. With dozens of antennas, the number of pairs becomes large. For each pair, the correlator measures relationships in the signal across many frequency channels. The results are later calibrated and processed into spectra, maps, or three-dimensional data sets that include two directions on the sky and one frequency or velocity axis. ALMA's official explanations describe the correlator as the system that allows the antennas to function together as a single scientific instrument. The atmosphere continues to cause trouble even at Chajnantor. Pockets of water vapor can delay the incoming waves by slightly different amounts above different antennas. If those delays are not corrected, the combined signal loses sharpness. Each antenna therefore carries a water vapor radiometer that measures emission from atmospheric water, along the same direction as the astronomical observation. Those measurements help estimate and correct the changing delay. Astronomers also observe calibration sources. A bright quasar with a well-understood compact signal can be used to measure how the atmosphere and electronics alter the phase and amplitude of the data. Other calibrators help establish the frequency response and overall flux scale. The telescope moves between the science target and suitable calibrators according to a planned sequence. Calibration may sound like preparation for the real observation, but it is part of the observation. Without it, a faint feature can be shifted, blurred, weakened, or mistaken for something it is not. Weather determines which observations are possible. Shorter submillimeter wavelengths are especially vulnerable to atmospheric water vapor, so the driest conditions are reserved for programs that need them. Other projects can proceed when conditions are less exceptional. ALMA commonly uses flexible scheduling, selecting observations that match the weather, array configuration, target position, and technical readiness at a given time. An astronomer may submit a project months before the data are collected and may not be present when the observation happens. This is different from the older image of someone standing at a telescope eyepiece through the night. ALMA has no eyepiece, and a person beside one antenna would not see the signal it was measuring. Observations are controlled electronically, and the resulting data must pass through several stages before they become scientifically useful. Staff monitor the array, check the weather, operate the antennas, assess data quality, and respond when a system behaves unexpectedly. The fact that the astronomer who requested the observation may be on another continent does not make the process automatic. It means that many specialists perform the work on the astronomer's behalf. ALMA is an international facility. Its construction and operation involve organizations in Europe, North America, East Asia, and Chile. The observatory joins different antenna designs, receiver systems, software, engineering teams, data centers, and support networks into one program. That arrangement adds organizational complexity, but it also spreads the enormous cost and technical effort of the facility across several partners. The array began early scientific observations with a partial set of antennas in 2011 and was formally inaugurated in 2013. Its scientific role is often described as studying the cold universe. Cold objects can be faint in visible light while emitting strongly at millimeter or submillimeter wavelengths. Dense clouds where stars form, dust around young stars, gas in distant galaxies, molecules in interstellar space, and material around evolved stars all become accessible in this range. The word cold is relative. Some spectral lines come from ionized regions with energetic conditions, but the radiation reaching ALMA is still measured at long wavelengths that optical telescopes do not detect. ALMA can observe both broad continuum emission and narrow spectral lines. Continuum radiation extends across a range of frequencies and is often associated with dust or other emission processes. A spectral line occupies a much more specific range. It appears when an atom, ion, or molecule changes between allowed energy states and emits or absorbs radiation at a characteristic frequency. Because the characteristic frequency can be measured in laboratories and calculated from atomic physics, the line serves as an identifier. If an oxygen line has a known rest frequency, astronomers know where it would appear in a nearby source. In a distant galaxy, cosmic expansion shifts it to a lower observed frequency. Measuring the shifted position gives the redshift. The width and shape of the line can also reveal motion. Gas rotating, flowing outward, falling inward, or moving randomly produces small changes in frequency through the Doppler effect. This is where ALMA's name becomes directly relevant to JADES-GS-Z14-0. The oxygen feature used in the discovery is the 88 micrometer line of doubly ionized oxygen, written as 0388 micrometers. In the galaxy's own frame, that line belongs to the far infrared part of the spectrum. The expansion of the universe stretched it until ALMA received it at a frequency near 223.5 GHz, corresponding to a wavelength of roughly 1.3 millimeters. The measured frequency gave a redshift of about 14.179. That redshift measurement was far more precise than the previous estimate from Webb's near-infrared spectroscopy. This was not because Webb had failed. The instruments were measuring different features under different conditions. Webb had already provided strong evidence that the galaxy lay at an exceptional distance. ALMA targeted a narrow frequency range where the redshifted oxygen line was expected. Once the line appeared clearly, its central frequency fixed the redshift with much smaller uncertainty. One study reported that the ALMA result improved the redshift precision by more than a factor of 180. The observation required less than 3 hours of integration time in the reported program. That may sound surprisingly brief for a signal that travelled more than 13 billion years, but the short duration does not include the decades of planning, construction, receiver development, calibration work, software design, and earlier observations that made the measurement possible. Telescope time is the visible end of a much longer chain. The oxygen line was detected at a significance of about 6.6 sigma. Sigma is a way of describing how strongly a measurement stands above the expected random noise. It is not a guarantee that every interpretation is correct, but a 6.6 sigma line is treated as a robust detection under the assumptions of the analysis. Two teams independently analysed ALMA data and both reported the oxygen feature at essentially the same frequency and redshift. Agreement between separate analyses strengthened the case. It is worth pausing over what the array physically received. No antenna recorded a spoken message from the galaxy, and the observatory was not literally listening in the way an ear listens. Radio astronomy often uses the language of listening because both sound and radio can be represented as waves, frequencies, and signals. But sound requires matter through which pressure changes can travel. The space between galaxies is far too thin to carry an audible sound to Earth. ALMA measured electromagnetic radiation, which can cross a vacuum. The final spectrum is therefore a visual representation of radio data. Frequency runs along one axis, and signal strength runs along another. The oxygen line appears as a rise above the surrounding noise. Astronomers may convert the frequency width into a velocity width, map the emission across the source, or compare it with observations at other wavelengths. The line becomes useful because it can be measured, not because it sounds impressive when converted into audio. ALMA also did not observe the galaxy with the kind of detail seen in an artist's impression. Images released with discoveries often combine real data, colour coding, enlarged insets, and artwork intended to communicate the subject. The actual galaxy is extremely faint and compact. The scientifically important result may occupy only a small region of a map and a modest feature in a graph. This is normal. Astronomy is not limited by whether the evidence looks dramatic to the eye. For JADES-GS-Z14-0, ALMA's contribution was precise and specialised. Webb established much of the galaxy's broader identity through infrared observations. ALMA detected the oxygen line, refined the distance, and provided information about the ionized gas. The observatories did not compete to produce the same result. They supplied different pieces of evidence. Modern astronomy frequently works this way because no single telescope can measure every wavelength with equal sensitivity and resolution. A visible light observatory cannot simply adjust a setting and become a millimeter array. Mirrors, antennas, detectors, atmosphere, cooling, timing, and data analysis all depend on wavelength. Webb operates above Earth's atmosphere and is optimized for infrared light. ALMA remains on the ground and uses many steerable radio dishes. Each design gives access to information the other cannot collect in the same manner. One might ask why ALMA was not placed in space as well. Removing the atmosphere would improve access to many wavelengths, but launching dozens of large antennas, deploying them across kilometre-scale separations, moving them between configurations, maintaining cryogenic receivers, and operating a correlator in orbit would be vastly more difficult and expensive. The Chajinantor site is a compromise that works remarkably well. It leaves some atmospheric limitations in place while allowing a large, adaptable instrument to be built, repaired, upgraded, and used for many years. The array's adaptability will matter as astronomers return to JADES-GS-Z14-0. Deeper observations could search for weaker lines, improve limits on dust emission, and map the oxygen with finer detail. Different configurations could test whether the gas is compact, extended, rotating, or disturbed. Other spectral lines could reveal colder gas or different ionization conditions. A first detection answers one question and creates a queue of more specific ones, which is one of science's more reliable habits. ALMA also makes surveys of other distant galaxies possible. If oxygen lines are found repeatedly at similarly early times, researchers can estimate how common rapid enrichment was. If they are rare, JADES-GS-Z14-0 may represent an unusual path through early galaxy formation. Either result would be useful. The distinction cannot be settled by looking harder at one object alone. The array in the desert therefore acts as more than a large radio camera. It is a measuring system built to preserve tiny timing differences, separate frequencies, correct atmospheric delays, and combined signals from many antennas. Its value lies in precision. The oxygen discovery depended on knowing where a line should fall, scanning the correct frequencies, identifying a statistically strong feature, and connecting that feature with atomic physics and cosmic expansion. Once all of those steps are understood, the detection no longer seems like ALMA somehow spotted oxygen floating in an empty part of the sky. The array measured radiation emitted by ionized oxygen inside a distant galaxy. Expansion shifted the radiation into ALMA's observing range. Interferometry provided sensitivity and spatial information. Spectroscopy supplied the identifying line. Calibration separated the astronomical signal from the effects of atmosphere and equipment. Analysis converted the result into a redshift and a physical interpretation. The observatory explains how the evidence reached us, but it does not yet explain why the oxygen was there so soon. For that, we need to leave the plateau and consider the universe before the first generations of stars had enriched it. The early universe was extremely hot, extremely dense, and expanding rapidly. There were no stars, galaxies, planets, rocks, oceans, or clouds of oxygen. There were not even complete atoms at first. Matter existed as a mixture of energetic particles, while light repeatedly interacted with charged material and could not travel freely across great distances. As the universe expanded, it cooled. This cooling allowed stable protons and neutrons to exist, and those particles became the basic components of atomic nuclei. A proton carries a positive electric charge. A neutron carries no net electric charge. The number of protons in a nucleus determines which element it is. 1 proton gives us hydrogen. 2 protons give us helium. 8 protons are required for oxygen. That last number is important. The early universe could assemble the lightest nuclei, but it did not remain in the right condition long enough to build large quantities of nuclei as complicated as oxygen. Expansion was reducing the temperature and density all the time. The cosmic kitchen was open for only a few minutes, and the menu was limited. During this brief period known as Big Bang nucleosynthesis, protons and neutrons collided and combined. Most hydrogen nuclei remained as individual protons. Some protons and neutrons formed deuterium, which is a heavier form of hydrogen. Further reactions produced helium-3 and helium-4, along with small amounts of lithium and other very light nuclei. By roughly 5 minutes after the Big Bang, the universe had cooled and expanded enough that this first major period of element formation was effectively over. It is easy to picture nucleosynthesis as though tiny finished atoms were being assembled. At that stage, however, the universe was still much too hot for electrons to remain attached to nuclei. What formed during the first minutes were mainly bare nuclei. A helium nucleus might exist, but it did not yet have the 2 electrons that would make it a neutral helium atom. Free electrons continued moving through the hot plasma and scattering photons. The distinction between a nucleus and an atom can feel rather technical, but it matters when we discuss early cosmic history. A nucleus contains protons and neutrons. An atom consists of a nucleus surrounded by electrons. The chemical behavior we associate with an element depends heavily on those electrons. Without them, there were no ordinary hydrogen atoms joining into molecules, no helium atoms drifting calmly through space, and certainly no oxygen chemistry. Why did Big Bang nucleosynthesis stop with such a small collection of light elements? Part of the answer involves falling temperature and density. Nuclear reactions need particles to meet with enough energy to overcome their electrical repulsion. Positively charged nuclei do not naturally welcome one another. They behave a little like 2 people, both trying to avoid taking responsibility for a group project. Getting them close enough to combine requires extreme conditions. The other difficulty involves unstable steps in the nuclear pathway. There are no stable nuclei containing exactly 5 or 8 nucleons. With a nucleon meaning either a proton or a neutron, this creates bottlenecks. A simple chain of adding 1 particle at a time cannot move smoothly from helium toward carbon and oxygen. Stars later overcome these obstacles by maintaining high temperatures and densities for much longer periods. The expanding early universe did not provide that luxury. The result was a cosmos composed overwhelmingly of hydrogen and helium, with only trace quantities of lithium and a few related light isotopes. By mass, ordinary matter was roughly 3/4 hydrogen and 1/4 helium, though the exact way that ratio is stated depends on whether we are counting mass or individual nuclei. Hydrogen nuclei are much lighter and much more numerous. Oxygen, carbon, nitrogen, silicon, and iron were absent in any significant primordial quantity. For hundreds of thousands of years, the universe continued to expand and cool. The nuclei and electrons remained part of an ionized plasma. Photons could not travel far without scattering from free charged particles, so the universe was opaque in much the same sense that a dense fog is opaque. Light existed everywhere, but it could not move directly across the cosmos without constant interruption. About 380,000 years after the Big Bang, the temperature had fallen enough for electrons to remain bound to nuclei. Protons captured electrons and became neutral hydrogen atoms. Helium nuclei did the same with the appropriate number of electrons. Cosmologists call this period recombination, even though the particles were combining for the first time. The name is one of those historical scientific terms that becomes easier to accept once one stops expecting it to behave literally. As free electrons became attached to nuclei, photons were able to travel much more freely. The light released from that period has been stretched and cooled by the expansion of the universe and is now observed as the cosmic microwave background. Instruments measure this background radiation across the sky, providing a picture of the universe when it was still less than 500,000 years old. The formation of neutral atoms did not immediately produce stars. The universe became transparent, but it remained dark in another sense. There were no concentrated sources of starlight. Matter was spread through space in a mostly smooth distribution of hydrogen and helium gas, along with dark matter that did not emit light but contributed gravity. Mostly smooth does not mean perfectly smooth. Small differences in density had existed from very early times. Some regions contained slightly more matter than others. Gravity gradually amplified those differences. A region with a little more matter exerted a little more gravitational attraction, drawing in additional material and increasing its advantage. Over millions of years, small variations developed into denser concentrations. Dark matter played a major role in this process. It does not interact with light in the ordinary way, so it could begin forming gravitational structures without being slowed by the same radiation effects that influence normal gas. Ordinary matter then collected within regions where dark matter had created deeper gravitational wells. Hydrogen and helium gas flowed inward, became compressed, and started the long process that would produce the first stars and galaxies. This interval after recombination and before the appearance of the first stars is known as the cosmic dark ages. It was not empty. Gas was moving, density structures were developing, and gravity was steadily gathering matter. But there were no stars to provide visible or ultraviolet light. The main material available was chemically primitive gas. No dust grains helped it cool. No carbon or oxygen atoms provided the rich range of radiation processes found in later gas clouds. Cooling is essential to star formation. A cloud of gas cannot simply fall inward without limit. As it contracts, gravitational energy is converted into heat. Rising pressure can resist further collapse. The gas must release some of that heat as radiation if it is to continue becoming denser. Modern star-forming clouds contain molecules, dust, carbon, oxygen, and other ingredients that provide efficient ways to cool across a wide range of temperatures. Primordial gas had far fewer options. Hydrogen atoms can emit radiation under certain conditions, and small quantities of molecular hydrogen can form even without dust, but the process is less efficient than cooling in chemically enriched gas. Computer models therefore suggest that the earliest collapsing clouds tended to remain warmer than many star-forming clouds today. Warmer gas has greater pressure, and larger amounts of material are needed before gravity can overcome that pressure. For this reason, many models predict that the first stars were generally more massive than typical stars forming in the present universe. Astronomers call this first-generation population 3 stars. The name does not mean that 2 earlier populations existed before them. Stellar population labels were assigned in historical order based on observed stars. Population 1 refers to relatively metal-rich stars such as the Sun. Population 2 refers to older, metal-poor stars. The hypothetical first metal-free generation was therefore given the next available number, population 3. Astronomy occasionally arranges its filing cabinet backwards and expects everyone to keep up. No confirmed population 3 star has yet been observed directly. Their properties are inferred from simulations, nuclear physics, the chemical patterns found in extremely old stars, and the effects that the earliest luminous objects had on surrounding gas. Researchers are confident that the first stars formed from hydrogen and helium with very small traces of lithium, but their usual masses, rotation rates, multiplicity, and final outcomes remain active questions. Recent theoretical work suggests that they may have formed in small groups with a broader range of masses than earlier simple models assumed. The first stars probably began appearing somewhere around 100 million years after the Big Bang, although the precise timing is uncertain. Dense clumps of primordial gas collapsed under gravity. Their centres became hotter and more compressed. When the central temperature and pressure became high enough, nuclear fusion began. Hydrogen fusion does not mean that 2 ordinary hydrogen atoms simply touch and become helium. The process occurs in stages and involves nuclei rather than complete atoms. In stellar interiors, temperatures are high enough that electrons are separated from nuclei. Hydrogen nuclei, which are protons, participate in reaction chains that eventually produce helium nuclei and release energy. Fusion releases energy because the final nucleus has slightly less mass than the original collection of particles. The missing mass is converted into energy according to Einstein's relationship between mass and energy. That energy pushes outward and helps support a star against gravity. A stable star spends much of its life in a balance between inward gravitational compression and outward pressure connected to energy production. The first metal-free stars had to begin their lives without carbon, nitrogen, or oxygen. Modern massive stars can use a hydrogen fusion pathway called the CNO cycle, in which carbon, nitrogen, and oxygen nuclei act as participants that help convert hydrogen into helium. Population 3 stars initially lacked those nuclei, so they had to rely on other reactions. Their cores could contract to higher temperatures until enough carbon was eventually created to allow the CNO cycle to contribute. This brings us to the first step toward oxygen. Hydrogen fusion gradually increases the amount of helium in a star's core. When the central hydrogen supply becomes depleted, gravity compresses the core further. The temperature rises. Under sufficiently hot and dense conditions, helium nuclei can begin to fuse. A helium-4 nucleus contains 2 protons and 2 neutrons. It is also called an alpha particle. 2 helium nuclei can briefly form beryllium-8, but beryllium-8 is extremely unstable and usually breaks apart almost immediately. In a hot, dense stellar core, a 3rd helium nucleus can sometimes collide with that unstable beryllium before it decays. The 3 helium nuclei then produce carbon-12. This is known as the triple alpha process. Once carbon exists, another helium nucleus can combine with a carbon-12 nucleus to produce oxygen-16. Carbon contains 6 protons, helium contains 2. Together they provide the 8 protons that identify oxygen. The reaction also releases a photon. This carbon plus helium process is one of the central reactions in stellar helium burning, and its rate strongly influences how much carbon and oxygen a star produces. The oxygen detected by ALMA therefore had a history inside stars. It could not have formed directly from cooling hydrogen gas in open space. The gas first had to collapse, stars had to ignite, hydrogen had to become helium, Helium had to produce carbon. Carbon had to capture additional helium nuclei and become oxygen. The oxygen then had to leave the stellar interior and enter the gas where ALMA's spectral line could reveal it. Massive stars can complete these stages much faster than stars like the Sun. A star's large supply of fuel does not guarantee a long life, because its core consumes that fuel at a much higher rate. The most massive stars can live for only a few million years. Some theoretical examples of very massive metal-free stars have lifetimes shorter than 1 million years. This speed is essential when considering a galaxy seen less than 300 million years after the Big Bang. There was time for several generations of short-lived massive stars, even though there was not time for Sun-like stars to complete their much slower evolution. Producing oxygen inside a star is only part of the problem. The element must also be released. If every oxygen-rich star quietly locked its material inside a black hole, the surrounding galaxy would remain chemically primitive. Different stars can end their lives in different ways depending on their mass, composition, rotation, internal mixing, and mass loss. Many massive stars undergo core collapse. Fusion continues through a sequence of heavier fuels until the central region can no longer generate enough energy to support the star. The core collapses rapidly, and the event may produce a supernova explosion. Material from the outer parts of the star can be expelled into surrounding space at high speed. This material contains elements that were present before the star formed and new elements produced during its life. Some of the first stars may have ended as pair instability supernovae, explosions that can completely disrupt a star without leaving a neutron star or black hole. Others may have collapsed directly into black holes and released relatively little of their heavy element content. Still others may have produced more familiar core collapse supernovae. The balance among these outcomes is uncertain, and it affects how rapidly the first galaxies could enrich their gas. Stellar winds can also remove material before the final collapse. Massive stars produce strong radiation fields and can lose gas from their outer layers. Metal-free stars may have behaved differently from metal-rich stars, because heavy elements affect how radiation transfers momentum to stellar gas. Rotation and binary interaction can complicate the process further. Two stars exchanging material can expose processed layers, alter lifetimes, and change the eventual explosion. Once oxygen-rich material leaves a star, it does not spread evenly through an entire galaxy at once. A supernova creates an expanding shock wave that heats, compresses, and stirs nearby gas. Some enriched material mixes with the surrounding medium. Some may escape from a small galaxy if the explosion is strong enough and the galaxy's gravity is weak. Other material may remain concentrated near the site of the explosion. The first enrichment was probably uneven. One region could contain gas touched by several supernovae, while another nearby region remained almost chemically pristine. Later stars formed from mixtures with different histories. This is why very old stars in the Milky Way can preserve unusual patterns of chemical elements. Their compositions may reflect the output of only a small number of earlier explosions. A modest amount of carbon and oxygen could change the way gas cooled. These elements have electronic structures that allow them to emit radiation efficiently at particular wavelengths. Dust created from heavy elements can provide additional cooling and surfaces on which molecules form. Cooler gas can break into smaller clumps, helping produce stars with lower masses. Chemical enrichment therefore does more than add new entries to a list of ingredients. It changes the physical process of star formation. Astronomers often describe this development using metallicity. As mentioned earlier, every element heavier than helium is called a metal in astronomical language. A cloud containing carbon and oxygen is metal-enriched, even if it contains nothing that would look metallic in daily life. The metallicity can be compared with that of the Sun, whose composition provides a convenient reference. The first stars had essentially zero metallicity. Gas affected by the first supernovae had a very low but non-zero metallicity. Each later round of star formation and stellar death could add more heavy elements. The process was not a simple universal increase at the same rate everywhere. Galaxies gained gas, lost gas, merged, formed stars in bursts, and experienced explosions that moved material between regions. This uneven development matters for JADES-GS-Z 14-0. Detecting oxygen does not mean that every part of the galaxy had the same chemical composition. ALMA measured emission from ionized oxygen in gas that was producing a detectable line. The observation reveals that enrichment had occurred, but it does not provide a complete inventory of every oxygen atom or a perfectly uniform metallicity map. It also helps to separate oxygen atoms from oxygen molecules. On Earth, oxygen in the atmosphere commonly appears as O2, with two oxygen atoms bound together. The early galaxy's detected line came from O3, meaning oxygen that had lost two electrons. The Roman numeral describes the ionization state used in spectroscopy. O1 refers to neutral oxygen, O2 to oxygen missing one electron, and O3 to oxygen missing two. Removing two electrons requires energetic radiation. Young, massive stars produce large amounts of ultraviolet light capable of ionizing surrounding gas. The O3 line therefore indicates that oxygen was present in an active environment influenced by hot stars. It does not merely tell us that one earlier generation had manufactured the element. It also connects the oxygen to ongoing or recent star formation within the galaxy. Those early stars affected hydrogen on much larger scales as well. Ultraviolet radiation removed electrons from neutral hydrogen atoms, beginning the long period known as cosmic ray ionization. Bubbles of ionized gas grew around stars and galaxies. As more sources appeared, these bubbles expanded and overlapped. The universe, which had become neutral after recombination, gradually became ionized again across much of intergalactic space. JADES-GS-Z 14-0 existed during this broad transition. Its stars were not operating in the calm, chemically mature environment of the present-day Milky Way. They were forming while galaxies were still assembling rapidly, and while radiation from early objects was changing the gas between them. The galaxy's oxygen had to be made within that limited timetable. The first stars might have appeared near the 100 million year mark, although their exact starting date is not known. The light from JADES-GS-Z 14-0 was emitted when the universe was around 300 million years old. That leaves perhaps a couple of 100 million years for gas to collapse, stars to form, massive stars to die, oxygen to spread, and new stars to continue ionizing the enriched gas. It is enough time for these events to occur, but the apparent degree of development makes the schedule demanding. Not every part of this history must have proceeded one step at a time across the whole galaxy. Star formation can happen in many regions at once. Massive stars can enrich their surroundings within a few million years. New stars can begin forming from partly enriched gas while other stars are still alive. Several overlapping cycles may operate rather than one neat generation politely waiting for the previous generation to finish. Even with that overlap, the ALMA result indicates rapid processing of material. The universe supplied hydrogen, helium, gravity, dark matter, and time. The galaxy converted part of that simple starting material into stars. Those stars created oxygen. Stellar deaths and outflows returned it to the gas. Energetic radiation then produced the ionized state that emitted the observed line. This is the chemical contrast behind the discovery. The Big Bang produced the raw material, but not the oxygen. Stars produced the oxygen, but they needed structures in which to form. Galaxies organized the gas, retained at least some of the enriched material, and supported repeated star formation. ALMA detected evidence that this chain was already well underway at an age when astronomers expected many galaxies to remain much less developed. The early universe was chemically simple only at the beginning. Once the first stars appeared, the simplicity did not last. A few million years of stellar activity could introduce carbon and oxygen. Explosions could spread those elements through young galaxies. Cooling could become more efficient. Later stars could form differently from the first ones. Each cycle changed the conditions for the next. That progression brings us from the nearly pure hydrogen and helium of the cosmic dark ages to one specific object whose light left before the universe reached 300 million years of age. It was first recognized through exceptionally deep observations, and its brightness immediately raised questions about how a galaxy could grow so quickly. The oxygen signal later detected by ALMA made those questions more difficult, because the object was not merely present at an early time, it had already formed enough stars and processed enough material to leave a measurable chemical signature across more than 13 billion years of expanding space. That measurable chemical signature belonged to JAD ES-GS-Z14-O, an object whose catalogue name is far less memorable than the circumstances in which it was found. It appears in a region of the sky associated with the constellation Fornax, within one of the deepest areas examined by the James Webb Space Telescope. To an ordinary eye, there is no visible galaxy waiting there. Even in Webb's carefully processed images, the source is a tiny, faint patch. Its importance comes from the distance encoded in its light, and from the fact that it was already unusually bright when the universe was less than 300 million years old. The first part of the name, JADES, stands for the JWST Advanced Deep Extragalactic Survey. This is a major observing program that uses Webb to study very distant galaxies through deep imaging and spectroscopy. The letters GS identify the good south field, a part of the sky that astronomers have observed repeatedly with several space telescopes. The final portion, Z14-O, marks the object as a candidate associated with a redshift near 14. Catalogue labels are designed to keep large datasets organised, not to sound elegant in narration. The universe may contain dramatic events, but the filing system remains practical. JADES was built to examine a period often called cosmic dawn, when the first generations of galaxies were forming and changing rapidly. Webb's large mirror and infrared instruments make it especially useful for this work. Light from very early galaxies begins largely in ultraviolet and visible wavelengths, but the expansion of the universe stretches it into the infrared before it reaches us. A telescope that detects infrared radiation can therefore see objects whose original light has been shifted far beyond the range of human vision. Finding such a source begins with images taken through several filters. Each filter records a different range of wavelengths. Astronomers compare how bright an object appears in one filter with how bright it appears in another. A very distant galaxy may be absent in the shorter wavelength images and then appear suddenly in longer wavelength ones. This pattern can indicate that the galaxy's light has encountered a strong spectral break. The relevant feature is the Lyman alpha break. Hydrogen absorbs photons with wavelengths shorter than a particular limit associated with the Lyman alpha transition. In a very distant galaxy, neutral hydrogen inside the galaxy, around it, and throughout the intervening universe removes much of the shorter wavelength light. The spectrum can therefore show little or no detected flux on one side of the break and a measurable continuum on the other. Cosmic expansion shifts the position of that break toward longer wavelengths, so its observed location provides an estimate of redshift. JADES-GS-Z14-0 display this dropout pattern in Webb's near-infrared camera data. The initial interpretation was not completely straightforward. A foreground galaxy sat only about 0.4 arc-seconds away in projection. That nearby looking neighbour was actually at redshift 3.475, still very distant by everyday standards, but much closer than JADES-GS-Z14-0. Its own spectral features could potentially contaminate measurements of the faint source beside it. The situation was made more awkward because the foreground galaxy's ALMA break appeared near a wavelength that could be confused with the expected Lyman break of a much more distant object. A ALMA break is produced by hydrogen in stellar atmospheres and can make an older, lower redshift galaxy resemble a very high redshift candidate when only a limited set of filters is available. Astronomers are cautious about this problem because an object that appears to come from the first few 100 million years can occasionally turn out to be a less distant galaxy, wearing an inconveniently similar set of colours. At one stage, JADES-GS-Z or 14-O was therefore treated as a possible low redshift interloper with an unusual spectral energy distribution. Its inferred brightness at the extreme high redshift solution also seemed difficult to explain. A galaxy that bright should have been rare at such an early time, which made the alternative interpretation worth taking seriously. Good science does not reward a result merely for being exciting. The dull explanation must be tested with equal care, even when the exciting explanation has already begun choosing its photograph for the announcement. Additional Webb observations changed the balance of evidence. The JADES Origins field program obtained deeper near-infrared camera images using medium-band filters. Broad filters collect light across relatively wide wavelength ranges, while medium-band filters divide the spectrum more finely. The added measurements trace the shape of the source's light with greater precision and strongly disfavored the low redshift explanation. The object behaved much more like a galaxy beyond redshift 14 than a closer contaminant. Imaging alone could still leave uncertainty, so the team used Webb's near-infrared spectrograph, or NIR spec. Unlike an image, which records where light appears, a spectrum records how the light is distributed by wavelength. NIR spec can observe many targets during one program through a system of tiny shutters. For JADES-GS-Z14-O, the spectrum showed a clear rise in detected flux around 1.85 micrometers, with no comparable signal on the shorter wavelength side. That sharp transition matched the expected Lyman alpha break at a redshift near 14. The researchers also measured the foreground neighbour separately. Its emission lines confirmed that it lay at redshift 3.475 and showed that its ALMA break could not account for the sharper break, observed at 1.85 micrometers in JADES-GS-Z14-0. The two objects happened to lie close together on the sky, but they belong to very different periods of cosmic history. The NIR spec analysis produced a redshift of 14.32, with an uncertainty extending slightly above and below that value. Later, ALMA detected the far infrared oxygen line and refined the redshift to about 14.1793, with a much smaller uncertainty. The slight numerical change did not move the galaxy into an ordinary category. It still represented a time less than 300 million years after the Big Bang. The improvement mattered because a well-defined spectral line gives a more exact systemic redshift than the broad shape of an absorption break. Redshift is commonly written with the letter Z. A value of 0 would mean no cosmological stretching. A value of 1 means that the observed wavelength is twice the emitted wavelength. At a redshift a little above 14, the observed wavelength is more than 15 times the wavelength at which the radiation was produced. Light emitted in the ultraviolet can arrive in the infrared, while far infrared emission can arrive in ALMA's millimeter range. The number does not act as a simple distance label under every circumstance. Converting redshift into age or distance requires a cosmological model that describes the expansion history of the universe. Using the standard model and measured cosmological parameters, the light from JADES-GS-Z14- was emitted when the universe was roughly 290 to 300 million years old. It then travelled for about 13.4 billion years before reaching the telescopes that recorded it. The phrase 13.4 billion light-years away is often used informally, but cosmic distance has several definitions because space expanded while the light was travelling. The galaxy's present-day co-moving distance, assuming it still exists as a distinct object, would be much larger than 13.4 billion light-years. For the present story, the most useful quantity is the look-back time. We are receiving information that left the galaxy about 13.4 billion years ago. At the time its confirmation was announced in 2024, JADES-GS-Z14-O became the most distant spectroscopically confirmed galaxy known. It retained that position through the announcement of ALMA's oxygen result in March 2025. Astronomy continued to advance, and MOM-Z14 was later confirmed at a slightly higher redshift, so JADES-GS-Z14-O is no longer the current distance record holder. Its scientific importance did not vanish when another object moved a little farther up the list. The galaxy remains one of the earliest well-studied systems and the site of an exceptionally early oxygen detection. Distance was only the first surprise. JADES-GS-Z14-O was also bright in ultraviolet light. Its absolute ultraviolet magnitude was measured at about -20.81. The astronomical magnitude scale runs backwards, so a more negative value means a brighter object. Among roughly 700 JADES candidates beyond redshift 8 considered in the Discovery study, it was the third most ultraviolet luminous, despite belonging to a much earlier period than most of them. Brightness at cosmic dawn creates a problem because galaxies need matter, time, and active star formation to produce large amounts of ultraviolet radiation. Young, massive stars emit strongly in ultraviolet wavelengths. A luminous ultraviolet galaxy usually contains many such stars or a powerful active galactic nucleus around a feeding black hole. Either explanation requires a substantial physical system to be operating when the universe had only recently begun forming galaxies. Researchers therefore examined whether the light might be dominated by an active black hole. A compact accretion disk around a black hole can produce great luminosity from a region too small for Webb to resolve. If many unexpectedly bright early objects were actually black holes rather than star-filled galaxies, some of the apparent tension with galaxy formation models might be reduced. JADES-GS-Z14-O did not look like a single unresolved point. Careful modelling of the near-infrared camera images gave it a half-light radius of about 260 parsecs. A parsec is roughly 3.26 light-years, so 260 parsecs is about 850 light-years. The half-light radius encloses half of the measured light, not the entire galaxy. Fainter emission could be traced to scales approaching 1 kiloparsec in the analysis. By modern galactic standards, that is still compact. The Milky Way's stellar disk stretches across tens of thousands of light-years. Yet for a source less than 300 million years after the Big Bang, a resolved radius of hundreds of parsecs was significant. The extended light suggested that stars spread through the galaxy were producing most of the ultraviolet emission. A black hole might still have been present, but the observations argued against one dominant, unobscured active nucleus, supplying nearly all the brightness. The foreground neighbour mildly magnified JADES-GS-Z14-O through gravitational lensing. Mass bends the path of light, and a foreground object can make a background source appear brighter. In this case, the estimated magnification was less than a factor of 1.2. The effect helped slightly, but it could not explain away the galaxy's unusual luminosity. Even after accounting for lensing, the source remained remarkably bright. The colour of the ultraviolet continuum added more information. Astronomers describe the shape of that continuum with a quantity called the ultraviolet slope. JADES-GS-Z14-O had a measured slope of about -2.20. Such a blue spectrum is consistent with a young stellar population and relatively low dust attenuation. although nebular emission and other effects can influence the precise value. Dust absorbs and scatters ultraviolet light, usually making a galaxy look redder and dimmer. The early universe did not begin with dust, because dust grains require heavy elements produced by stars. Finding even modest signs of dust at redshift 14 would therefore be another indication that stellar processing had already occurred. Models of JADES-GS-Z 14-0 generally favour a small but non-zero amount of attenuation rather than a completely dust-free system. A separate Webb observation used the mid-infrared instrument, or MIRI, to detect the galaxy at 7.7 micrometers. At redshift 14, that observed wavelength corresponds to visible light in the galaxy's own frame. The MIRI measurement was brighter than a simple continuation of the shorter wavelength continuum would predict. The likely explanation was strong emission from hydrogen beta and visible wavelength doubly ionized oxygen lines entering the broad MIRI filter. This was not yet the direct far-infrared oxygen measurement later made by ALMA. MIRI recorded combined light through a filter, rather than separating a narrow oxygen line with the same precision. Even so, the excess brightness provided an early indication that ionized gas and heavy elements were present. Models combining the MIRI detection with the other Webb data suggested that at least a third of the 7.7 micrometer flux could come from hydrogen and oxygen emission lines. Estimating the galaxy's stellar mass and star formation history requires fitting models to all of these measurements. One plausible interpretation placed its stellar mass near 500 million times the mass of the Sun, and included a strong burst of star formation during the most recent few million years before the observed light was emitted. Other analyses produce somewhat different values because the age, dust content, metallicity, star formation history, and escape of ionizing radiation can trade off against one another in the models. The 500 million solar mass estimate should therefore not be imagined as a direct count of stars. Astronomers cannot resolve individual stars at this distance. They compare the combined spectrum and brightness with theoretical populations of stars of different ages and compositions. A young population can be extremely bright for its mass, while an older population contains more dim stars and can hide more mass. Dust can conceal light. Emission lines can raise the flux in particular filters. The answer is a probability distribution, not a receipt printed by the galaxy. Even with those uncertainties, every reasonable interpretation requires rapid growth. Gas had to collect in a dark matter halo, cool, fragment and form stars. Some stars had already lived long enough to enrich the surrounding gas. The galaxy was producing enough ultraviolet radiation to be seen across almost the full, observable history of the universe. Its stellar light was extended across hundreds of parsecs, rather than confined to one tiny source. The timing becomes easier to appreciate when compared with stellar lifetimes. Massive stars can live and die within a few million years. So many short cycles could fit inside the first 300 million years. Lower mass stars would still be near the beginning of their lives. JADES-GS-Z 14-. O did not need to wait for every kind of star to evolve. It needed an efficient sequence dominated by massive stars, rapid enrichment, and continued star formation. Its surroundings also mattered. The universe at redshift 14 was still substantially neutral. Ultraviolet photons from young stars encountered hydrogen that absorbed radiation below the Lyman alpha break. Some ionizing photons may have escaped the galaxy and contributed to an expanding bubble of ionized gas. Models used to fit the spectrum often require a significant escape fraction, although the exact value remains uncertain. Neutral gas near the galaxy can alter the detailed shape of the Lyman break. Once ALMA fixed the systemic redshift more precisely, researchers found that the Webb spectrum could be explained by a large column of neutral hydrogen, producing damped Lyman alpha absorption. This offered a possible view of the galaxy's immediate gas environment, not only its distance. A break that first served as a redshift clue became a clue about surrounding hydrogen after another observatory supplied the more precise redshift. The object also affected estimates of how common bright galaxies were at very early times. Pre-Webb surveys had limited sensitivity and usually suggested that the number of luminous galaxies should fall rapidly beyond redshift 10. JADES found more bright candidates than many of those extrapolations predicted. The spectroscopic confirmation of JADES-GS-Z14-0 showed that at least one of the most extreme candidates was not a lower redshift mistake. The Discovery study reported that the abundance of luminous galaxies at these epochs appeared more than 10 times higher than some extrapolations based on earlier observations. That comparison does not mean the standard cosmological model has been discarded. It means that the astrophysics connecting dark matter halos to visible galaxies may need adjustment. Star formation could have been more efficient. Bursts could have made galaxies temporarily brighter. Dust behaviour could have differed. The distribution of stellar masses might have favoured more massive ultraviolet bright stars. Another possibility is that surveys preferentially find the brightest moments in highly variable galaxies. A small early galaxy may spend much of its time faint, then become visible during a short burst of star formation. Observations would select the burst and miss the quieter periods. In that case, the galaxy's brightness would not represent a steady condition. It would represent the moment when the system happened to be easiest to detect. JADES-GS-Z14-0 may have experienced several such episodes. Models suggest that its stars could have begun forming around redshift 20, roughly 100 million years before the light we observe. Feedback from radiation and supernovae may have interrupted star formation, pushed gas outward, and then allowed new activity when material returned or fresh gas arrived. These histories are not directly filmed. They're reconstructed by testing which sequences can reproduce the observed mass, colour, size, emission, and gas properties. Its compact size would make feedback especially important. Massive stars release intense ultraviolet radiation and strong winds. Supernovae inject energy and momentum into the gas. In a shallow gravitational potential, those processes can drive material out of the central region or even out of the galaxy. Losing gas slows future star formation, but compression from shocks can also trigger new stars in other places. The same stellar population can both build a galaxy and interfere with its next stage of growth. This creates a useful caution. Describing JADES-GS-Z14-0 as mature does not mean it resembled a settled modern spiral galaxy. It had no known organised disk like the Milky Way, no measured spiral arms, and no reason to be dynamically calm. Early galaxies were likely irregular, gas-rich, frequently merging, and strongly affected by bursts and outflows. Chemical maturity refers to the unexpectedly advanced enrichment revealed by oxygen, not to a peaceful or completed structure. The object seen by Webb and ALMA may have changed greatly within only a few tens of millions of years after the observed moment. It could have merged with neighbouring systems, formed additional stars, lost gas, or developed a central black hole. Any later light showing those changes remains behind the radiation currently reaching us. We are examining one early frame from a much longer history. That frame is unusually informative because several instruments measured different parts of it. NIR-CAM located the source and mapped its colours and size. NIR-SPEC identified the Lyman break and established the high redshift interpretation. MIRI sampled rest frame visible emission and indicated strong ionized gas lines. ALMA then found the far infrared oxygen feature, fixed the redshift precisely, and supplied a direct measure of chemically enriched gas. The galaxy's former record status attracted public attention, but the more durable result lies in this combined evidence. JADES-GS-Z14-0 was present, bright, spatially extended, actively forming stars, and already enriched with oxygen within the universe's first 300 million years. None of those properties alone is impossible. Their combination, appearing so early and in one source, places demanding conditions on any model intended to explain it. A key step in the investigation focused on the ALMA spectrum itself. A narrow feature appeared near 223.5 GHz inside a section of the radio spectrum that the researchers had selected in advance. It was not found by asking ALMA to search every possible frequency across the sky. The observation was designed around a specific target, a specific atomic transition, and a range of possible distances already suggested by the James Webb Space Telescope. Webb's earlier spectrum had placed JADES-GS-Z 14-0 somewhere around a redshift of 14. The estimate was based mainly on the position and shape of the Lyman break, where neutral hydrogen had removed light below a certain wavelength. That break was strong enough to establish that the galaxy was extremely distant, but it could not give a perfectly exact redshift. Absorption by nearby gas inside the galaxy, motion, and the condition of the surrounding intergalactic medium can all affect the shape of the break. The Webb estimate was a little like knowing that a house lies somewhere along a particular road without yet knowing its number. Astronomers had a narrow enough region to search, but ALMA still needed to examine a range of frequencies rather than one single location. The expected oxygen line could appear at slightly different frequencies depending on the galaxy's exact redshift. The transition they chose was the 88 micrometer fine structure line of doubly ionized oxygen, written as O3. In its original frame, before cosmic expansion stretched it, the radiation had a wavelength of approximately 88 micrometers. The square brackets in the notation indicate a type of transition that is unlikely under ordinary dense laboratory conditions, but can occur in the thin gas found in space. Astronomers call such transitions forbidden lines, although nature has clearly not taken the name as a firm instruction. Doubly ionized oxygen is oxygen that has lost 2 electrons. Producing it requires energetic ultraviolet radiation, usually supplied by hot, young, massive stars. The line is emitted within ionized regions around those stars, where atoms and free electrons interact. It is also an important way for ionized interstellar gas to lose energy. For these reasons, the O388 micrometer line can reveal the presence of oxygen, while also providing information about active star formation and the physical conditions within a galaxy. This line was a sensible target for another reason. It can be bright in young, metal-poor galaxies with hard radiation fields. Galaxies in the early universe often contain recently formed massive stars, and those stars emit the energetic photons needed to create O3. The line had already been observed in galaxies at lower redshifts, giving astronomers models and comparisons that could help them interpret a detection at redshift 14. The uncertainty in the Webb redshift determined the range ALMA needed to cover. The observing program used 2 frequency settings, usually called tunings, with 3 spectral windows in each. Together, they provided continuous coverage from about 218.70 to 229.45 GHz. That frequency range corresponded to possible oxygen line redshifts between approximately 13.79 and 14.51. According to the researchers, the selected range covered about 98% of the redshift probability distribution derived from Webb's spectrum. They were not searching blindly. They knew which line they wanted, where the galaxy was located, and the range in which the line was very likely to appear. Still, there was no certainty that oxygen would be bright enough for ALMA to detect. Earlier attempts to find far-infrared lines in several galaxies beyond redshift 10 had often produced upper limits, or uncertain features rather than clear results. The observations were made through an ALMA director's discretionary time program. This type of observing time can be awarded to projects that are especially urgent or scientifically important, and cannot wait comfortably for the next normal proposal cycle. JADES-GS-Z14-0 had only recently been confirmed as an exceptionally distant galaxy, so a quick follow-up observation offered a rare opportunity. One tuning was observed in August 2024, and the other was observed in September. Each received about 2.8 hours of observing time. The conditions were good for one set and exceptionally dry for the other, with very low levels of precipitable water vapour above the array. At these wavelengths, dry weather is essential because atmospheric water absorbs and distorts the incoming radiation. Even in the Atacama Desert, astronomers must occasionally wait for the sky to become less enthusiastic about containing water. Different antenna configurations were used for the two tunings because of scheduling constraints. The longest baselines extended to hundreds of meters, providing enough resolution to separate the target from nearby features, while still maintaining sensitivity to the compact emission. The final resolution was not intended to produce a detailed portrait of individual star-forming regions. At this distance, even a small patch on the sky represents a large physical area. The primary objective was to find and measure the spectral line. Each ALMA antenna received faint radio waves from the direction of JADES-GS-Z14-0. The observatory then combined the signals from many antennas through interferometry. Before that combination could become reliable, the data had to be calibrated. Atmospheric conditions, receiver performance, antenna positions, timing, and the changing path of the signal through the air all needed correction. Astronomers observed bright calibration sources whose radio properties were better known. These observations revealed how the atmosphere and the instrument were modifying the signal at a particular time. Software then applied corrections to the target data. Measurements that failed quality checks could be removed. The remaining information was combined into a three-dimensional data cube. A data cube is not a physical cube sitting beside the telescope. It is a digital structure with two spatial dimensions and one frequency dimension. Each position in the image contains a small spectrum. Researchers can move through the frequency channels and see whether emission appears at the target position only within a narrow range. They can also add several channels together to improve the visibility of a line. Random noise appears throughout the cube. Some noise comes from the receivers, some from the atmosphere, and some from the fundamental limits of measuring a weak signal. The noise creates positive and negative fluctuations. A small positive bump is therefore not automatically a galaxy. Given enough frequency channels and enough positions, random data will eventually produce something that looks mildly interesting. This is one of the most important habits in observational astronomy. Researchers must ask not only whether a feature exists, but how often an equally strong feature could appear by accident. They examine the surrounding field, compare positive and negative fluctuations, change the way the channels are combined, and test whether the signal remains at the correct position. A convincing line should behave like astronomical emission, rather than like one fortunate arrangement of noise. In the spectral scan of JADES-GS-Z14-0, one feature stood out. It appeared at approximately 223.528 GHz in one analysis and 223.524 GHz in the other. The small difference came from slightly different methods of extracting and modelling the signal. Both values agreed within their uncertainties. More importantly, both independent teams found the feature at essentially the same frequency and at the position of the Webb galaxy. There was no collection of equally convincing features spread through the observed range. The schools-led analysis reported that only one signal in the scan could confidently be identified as O3 emission. Its position also agreed with a tentative carbon emission feature previously seen by Webb's NIR spec instrument. That earlier C3 feature had been detected at only 3.6 sigma, making it suggestive rather than decisive on its own. Its estimated redshift, about 14.178, nevertheless matched the much stronger ALMA line. The agreement mattered because unrelated errors are unlikely to point to the same redshift repeatedly. The Lyman break placed the galaxy broadly near redshift 14. The tentative carbon line suggested a much narrower value. ALMA then found the expected oxygen line at almost exactly that value. Each measurement used a different part of the spectrum and depended on different physical processes. The oxygen feature was detected at about 6.6 sigma. Sigma refers to the measured strength of a signal compared with the statistical noise. A 1 sigma feature is common and unpersuasive. 2 sigma may attract brief attention. 3 sigma can be interesting but still requires caution, especially when a large data set has been searched. 6.6 sigma is far more difficult to explain as a random fluctuation. That number does not mean there is a 6.6 out of 10 chance that the line is real. Sigma is not a simple confidence rating. Under an ideal Gaussian noise model, a fluctuation that far from the mean would be extraordinarily unlikely to occur at a specified position and frequency by accident. Real astronomical data can contain complications that do not follow ideal statistics, which is why researchers also inspect calibration, imaging choices, location, and consistency. In this case, the statistical significance was supported by the independent analyses and by the prior web measurements. The Carniani-led team reported a significance of 6.67 sigma and fitted the line at 223.524 GHz. The Scoos-led team reported 6.6 sigma and a central frequency near 223.528 GHz. One team described the redshift as 14.1796, while the other gave 14.1793. Both quoted an uncertainty of approximately 0.0007. The difference between those redshift values is much smaller than the earlier uncertainty from the Lyman break and has no meaningful effect on the broad physical picture. To convert the observed frequency into redshift, astronomers compare it with the known rest frequency of the oxygen transition. The 0388 micrometer line has a rest frequency of approximately 3.393 terahertz. ALMA received it at about 223.5 GHz. Dividing the rest frequency by the observed frequency gives the factor by which the wavelength has been stretched. Subtracting 1 gives the redshift. The resulting value means the wavelength expanded by a factor of a little more than 15 during its journey. Radiation that began at 88 micrometers arrived at roughly 1.34 millimeters. Nothing happened to the oxygen atom after it emitted the photon that could personally supervise this change. The expansion of space stretched the radiation as it travelled. With a redshift of 14.1793, cosmological models place the galaxy at an age of about 290 million years after the Big Bang. The light then spent approximately 13.4 billion years travelling toward the region of space where Earth would eventually form. During most of that journey, there was no Earth, no Sun, and no Atacama Observatory waiting for it. The precision of the new redshift was one of the major benefits of the detection. Webb's Lyman break estimate had been 14.32, with an uncertainty extending by about 0.20 below and 0.08 above. ALMA reduced the uncertainty by more than a factor of 180. The official announcement described the distance precision as about 0.005%, comparable to measuring 1 kilometre to within roughly 5 centimetres. Such precision affects more than the number printed beside the galaxy's name. Once the systemic redshift is known, researchers can place every other feature in the Webb spectrum into the correct rest frame position. They can reconsider the shape of the Lyman break, test whether neutral hydrogen near the galaxy caused additional absorption, and calculate which emission lines entered each imaging filter. A poorly known redshift can blur many derived properties. The estimated age of the universe changes slightly across the possible range. Luminosities depend on distance. The wavelengths assigned to spectral features change. Physical models may fit the same data differently, depending on where the galaxy sits. The ALMA line sharply reduced that freedom. The shape of the oxygen line supplied additional information. It was not infinitely narrow. Gas within a galaxy moves because of rotation, turbulence, outflows, gravitational motion, and the activity of young stars. Material moving toward us shifts its emission to a slightly higher frequency, while material moving away shifts it lower. The combined motion broadens the line. The Carniani-led analysis found that the feature was spectrally resolved, with a full width at half maximum of about 100 km per second. Full width at half maximum is a standard way to describe a line's width. Researchers locate half of the peak intensity and measure the distance between the two sides of the line at that level. A width near 100 km per second does not mean the whole galaxy is travelling toward or away from us at that speed. The central frequency gives the galaxy's overall recession through cosmic expansion. The width reflects the range of internal velocities within the emitting gas, combined with the spatial and spectral resolution of the observation. Using the line width and the estimated size of the galaxy, one team calculated a dynamical mass of roughly 1 billion solar masses with substantial uncertainty. Dynamical mass refers to the total mass needed to produce the observed motions, including stars, gas, and dark matter within the measured region. The result was comparable to some estimates of the stellar mass, leading that team to suggest that the central region might contain a surprisingly low fraction of gas. That interpretation is not the final word on the galaxy's gas supply. Later work using the strong neutral hydrogen absorption in the Webb spectrum argued that the galaxy could be embedded in a much larger reservoir of relatively pristine neutral gas. The oxygen line may trace enriched, ionized material in the compact star-forming center, while much of the surrounding gas remains less chemically processed. These observations can therefore describe different parts of the same system, rather than directly contradicting one another. The measured oxygen line luminosity was about 2.1 times 10 to the power of 8 solar luminosities. This does not mean that the galaxy contained 200 million suns made of oxygen. Luminosity measures the energy emitted per unit time in that particular line. Expressing it in solar luminosities simply provides a familiar astronomical unit. For its estimated star formation rate, the O3 luminosity fell within the broad relationship seen in galaxies in the local universe, although toward the lower end in one analysis. This was interesting because the galaxy lived under very different conditions from nearby systems. Its stars were young, its radiation field was intense, and the surrounding universe was still in an early stage of reionization. Yet the connection between oxygen line emission and star formation was not completely unfamiliar. Researchers also searched for continuum emission around the line. A spectral line is concentrated in a narrow frequency range, while continuum emission extends more smoothly across the observed band. At these wavelengths, continuum radiation can come from dust grains warmed by starlight. Detecting it would help estimate the amount and temperature of dust within the galaxy. No significant dust continuum was detected. The Scouse-led team used this non-detection to place an upper limit on the ratio of dust mass to stellar mass of less than about 2 parts in 1,000. The result was consistent with dust being produced by supernovae, provided that the surviving dust yield per event remained below about 3/10 of a solar mass under their assumptions. A non-detection is not evidence that the galaxy contained absolutely no dust. Dust could have been too faint, too warm, too cold, or distributed in a way that placed its emission below ALMA's sensitivity. The limit depends on an assumed dust temperature and emission model. At redshift 14, the cosmic microwave background was also much warmer than it is today, affecting both the heating of coal dust and the contrast against which its radiation would be measured. The oxygen line was easier to identify because atomic transitions are concentrated at known frequencies. Dust continuum is broader and can disappear more easily into noise. This difference allowed ALMA to make a strong chemical detection, while leaving the dust content only partly constrained. One might reasonably ask how the researchers knew the line belonged to oxygen rather than another atom or molecule at a different distance. Radio spectra contain many possible transitions. A single line can occasionally be ambiguous when the source redshift is unknown. Here, the prior information from Webb removed most of that ambiguity. JADES-GS-Z14-0 was already securely identified as a galaxy beyond redshift 14. At that redshift, the 88 micrometer oxygen transition should appear at the observed frequency. The line was located at the exact sky position of the galaxy, and its redshift matched both the Lyman break and the tentative carbon feature. An unrelated low redshift line would require another emitting object to lie in nearly the same position, and to produce a transition at exactly the measured frequency. The nearby foreground galaxy was known to be at redshift 3.475, and the expected positions of its common lines did not provide a convincing explanation for the ALMA feature. Two teams considered the evidence and independently identified the signal as O3. The line's location within the scan also helped. The observing program had covered almost all the probability range predicted by Webb, and only one feature met the criteria for a confident detection. It appeared where the earlier tentative carbon line suggested that it should. Random noise had not merely produced a bump somewhere in a broad search. It had apparently chosen the position, frequency and redshift already favoured by independent data, which would be an unusually organised performance for random noise. This combination is how ALMA recognised oxygen across 13.4 billion years. It did not recognise an image shaped like an oxygen atom. It did not separate one atom from the galaxy. It measured a narrow excess of electromagnetic radiation, compared its frequency with a laboratory-known atomic transition, confirmed its position, evaluated its statistical strength, and checked whether it agreed with observations made at other wavelengths. The result depended on a chain of knowledge stretching from atomic physics to cosmology. Laboratory measurements established the rest frequency. The theory of ionized gas explained where the line could form. Webb provided the location and approximate redshift. ALMA covered the predicted frequencies. Calibration preserved the faint signal. Statistical analysis showed that the feature stood well above the noise. Cosmological expansion connected 223.5 GHz at Earth, with an 88 micrometer emission line in the galaxy. Every part of that chain had to work. A small error in the target position could reduce the extracted signal. An incorrect redshift range could place the line outside the observed windows. Poor atmospheric conditions could raise the noise. Faulty calibration could produce misleading features. A weak line might remain invisible even if oxygen were present. The successful detection was therefore not inevitable. The signal was faint by ordinary standards, but faintness is not the same as uncertainty. Once many antennas observed for several hours and the measurements were combined, a reliable feature emerged. It occupied only a small portion of the spectrum, yet it reduced the galaxy's redshift uncertainty dramatically, and confirmed that oxygen existed during the universe's first 300 million years. The larger surprise did not come from the technical act of identifying the line. Massive stars can produce oxygen quickly, and theorists did not expect the early universe to remain completely oxygen-free until some fixed later date. The surprise came from the brightness of the line when combined with Webb's measurements of the galaxy's stars and visible oxygen emission. Models using the ALMA and Webb data estimated a gas phase metallicity of roughly 5 to 20% of the Sun's value in one study. The other analysis inferred a value above 10% of solar and obtained a preferred estimate near 17% when fitting the broader set of observations. These numbers depend on assumptions about the radiation field, density, star formation history, and the fraction of ionizing photons that escape, but all pointed towards substantial enrichment for such an early object. The line therefore carried two messages. The first was precise and direct: JADES-GS-Z 14-0 lies at a redshift of about 14.179. The second required physical modelling. The galaxy had already produced and distributed much more oxygen than many researchers expected to find at that age. That second message is where the discovery becomes difficult for existing timelines. Less than 300 million years after the Big Bang, the galaxy had progressed beyond its first chemically simple stars. It had formed massive stars, allowed them to manufacture oxygen, release that material into the surrounding gas, and continued producing the energetic radiation needed to ionize it. The oxygen feature was not a trace from one isolated stellar death. Its luminosity indicated an active enriched environment connected to significant star formation. When the researchers compared the galaxy with expectations for such an early period, they found something that appeared to have developed with unusual speed. A galaxy can be young in several different ways. It can be young because its first stars formed recently. It can be young because most of its gas has not yet been converted into stars. It can also be young because only a small number of stellar generations have had time to manufacture heavier elements. JADES-GS-Z14-0 satisfied the first definition by necessity. The universe itself was less than 300 million years old when the light we observe left the galaxy. The oxygen detection showed that it did not fit the other definitions nearly as well as expected. That mismatch led Sander Schools, the lead author of one of the ALMA studies, to compare the discovery with finding an adolescent in a place where only babies were expected. The comparison referred to chemical development, not to the galaxy having reached a finished or stable condition. JADES-GS-Z14-0 was still a compact, rapidly changing system. Its stars, gas and radiation were probably interacting in a far less orderly way than those in many nearby galaxies. Even so, it had completed several stages of chemical evolution unusually early. Before Webb and ALMA began examining galaxies from this period, many models predicted that the number of bright, massive systems would decline sharply as astronomers looked farther back in time. This expectation was reasonable. Earlier galaxies had less time to gather gas, form stars, and increase their stellar mass. Dark matter halos were generally smaller. Star formation could be disrupted by energetic radiation and supernova explosions. Heavy elements and dust, which later helped gas cool and form new stars, were only beginning to appear. A galaxy at redshift 14 was therefore expected to be small, chemically primitive, and difficult to detect. It might contain a first or second generation of stars, but it should not normally resemble a system that had already processed a substantial fraction of its gas through repeated stellar activity. There had simply been less time available for every required step. JADES-GS-Z14- challenged that expectation before ALMA detected oxygen. Webb found that it was remarkably bright in ultraviolet light, with an absolute ultraviolet magnitude of about -20.8. Its light was also spatially extended across hundreds of parsecs, suggesting that the brightness came mainly from stars spread through the galaxy, rather than from one unresolved active black hole. Estimates based on Webb observations suggested a stellar mass that could be around 500 million times the mass of the Sun, although the exact value depends on the assumed star formation history, metallicity, dust, and stellar population. None of those properties is impossible at an age of roughly 290 million years. The difficulty comes from producing all of them together. A dark matter halo had to form early enough to attract a large supply of ordinary matter. Gas had to fall into that halo instead of remaining spread through intergalactic space. It then had to lose energy, become dense, and break into star-forming regions. Those regions needed to produce enough massive stars to create the ultraviolet brightness measured by Webb. The process also had to survive its own consequences. Massive stars do not form quietly. They emit intense ultraviolet radiation, drive powerful winds, and eventually explode or collapse. In a small early galaxy, that energy can heat the remaining gas and push it outward. Some material may leave the star-forming region or escape the galaxy entirely. A burst of star formation can therefore reduce the supply needed for the next burst. Models of early galaxy formation must balance these competing processes. Gravity pulls gas inward. Cooling allows it to contract. Star formation turns part of it into stars. Radiation and explosions heat or expel part of what remains. Fresh gas can arrive from outside. Some expelled material may later fall back. The galaxy grows through repeated exchanges rather than through a smooth conversion of every available atom into a star. Pre-Webb predictions often assumed that this feedback would strongly limit the brightness and growth of the earliest galaxies. Small systems have weaker gravity, making it easier for stellar activity to disturb them. The first generations of stars may also have produced especially energetic radiation. If star formation stopped frequently, a galaxy would need more time to build a large stellar population. Webb began finding more luminous galaxies at very high redshift than many earlier forecasts had suggested. Spectroscopic confirmation was essential because some apparently remote candidates can be lower redshift galaxies whose colours imitate a Lyman break. JADES-GS-Z14-O survived that test. The discovery paper concluded that bright and massive galaxies existed about 300 million years after the Big Bang, with a number density more than 10 times higher than extrapolations based on pre-Webb observations. This does not mean that galaxies outnumbered predictions everywhere by exactly the same factor. Surveys cover limited areas, the earliest objects are difficult to find, and the measured number density is affected by selection methods and statistical uncertainty. The broader point is that the decline in bright galaxies toward earlier times appeared slower than many researchers had anticipated. Several explanations could increase the number of visible galaxies without changing the underlying cosmology. Early galaxies may have converted gas into stars more efficiently. Their star formation may have occurred in brief, intense bursts that temporarily made them easier to detect. Their stars may have produced more ultraviolet light for a given amount of stellar mass. They may have contained less dust than later galaxies, allowing more ultraviolet radiation to escape. Some sources may also have received modest help from gravitational lensing. JADES-GS-Z14-0 appears to include more than one of these effects. Its ultraviolet light indicates a young and active stellar population. The small amount of inferred dust attenuation allows much of that light to escape. Its foreground neighbour provides only weak magnification, not enough to explain the brightness. Webb's MIRI measurement also suggested a strong contribution from ionized gas emission lines, consistent with vigorous recent star formation and rapid enrichment. ALMA then added the oxygen line. Detecting oxygen by itself was not the most difficult part to explain. Massive stars can begin producing oxygen within a few million years. If the first stars formed early enough, some oxygen should already have existed by the time JADES-GS-Z14-0 emitted the observed light. The unexpected result was the estimated level of enrichment. The two ALMA studies, combined with the Webb data and photoionization models, indicated a gas phase metallicity somewhere around 5 to 20% of the Sun's value. One analysis preferred a value near 17%. The official ALMA announcement summarized the result by saying that the galaxy appeared to contain about 10 times more heavy elements than expected for such an early object. Metallicity values at this distance are not measured as simply as the temperature on a thermometer. Researchers compare several observations with models of ionized gas and stellar populations. They must assume or constrain the density of the gas, the hardness of the radiation field, the fraction of ionizing photons that escape, and the relative contributions of different emission lines. Changing those assumptions can shift the preferred metallicity. Even allowing for uncertainty, the oxygen abundance was too substantial to dismiss as a minute contamination from one early supernova. The galaxy's enriched gas had to represent a meaningful history of stellar processing. Stars had formed, produced oxygen, and released it into the surrounding medium. The material then mixed with gas that was still being illuminated by a powerful population of young stars. The Sun provides a useful comparison only if it is treated carefully. Saying that the galaxy had perhaps 10 or 20% of solar metallicity does not mean it was almost like the present Milky Way. The Sun formed more than 9 billion years after the Big Bang from gas enriched by many generations of stars. JADES-GS-Z14-0 remained much more metal-poor. The surprise lies in how far it had travelled from zero within the first few 100 million years. Consider the timetable. The universe became transparent about 380,000 years after the Big Bang, but the first stars did not appear immediately. Gas had to collect inside growing dark matter halos. Simulations generally place the onset of the first star formation tens or hundreds of millions of years later, depending on the mass of the halo and the local conditions. By the time of JADES-GS-Z14-0, perhaps around 290 million years after the Big Bang, only a limited interval had been available for galaxy building. Within that interval, at least one stellar generation had to complete its life. More likely, several overlapping generations were involved. Massive stars could die after only a few million years, making rapid enrichment possible. Lower mass stars would not yet have contributed much because they evolved too slowly. The early oxygen was therefore probably dominated by short-lived massive stars and their explosions or winds. Producing a metal is not the same as enriching an observable galaxy. Oxygen created in a stellar core remains hidden until it reaches the surrounding gas. A supernova may release it, but the explosion can also throw the enriched material out of a small galaxy. Retaining metals is difficult when gravity is weak and feedback is strong. JADES-GS-Z14-0 had to keep or recover enough of the oxygen for it to become part of a bright ionized region. If much of the metal-rich gas escaped, the galaxy needed an even greater amount of earlier star formation to reach the measured abundance. If the enriched material remained concentrated in the central region, ALMA may have sampled a chemically developed area embedded within a much more primitive reservoir. Either possibility requires a fast and active history. Later analysis has illustrated how complicated this gas distribution may be. One interpretation of the oxygen line width and the galaxy's compact size suggested a dynamical mass close to the estimated stellar mass, leaving relatively little room for gas in the central region. Another study of the strong neutral hydrogen absorption argued that the system could be surrounded by a much larger reservoir of relatively pristine gas. The enriched oxygen-emitting center and the neutral outer material may be tracing different components. This uneven structure would not be unusual in principle. Chemical enrichment begins locally. A group of massive stars can pollute the gas around them, while another region remains almost untouched. Supernova shocks stir the material, but mixing across an entire galaxy takes time. A telescope detecting one bright emission line is often most sensitive to the active, ionized regions, not to every quiet cloud surrounding them. The phrase chemically mature must therefore remain limited to what the evidence supports. It does not tell us that every part of JADES-GS-Z14-0 had a metallicity near 1/5 of the Sun's. It tells us that the observed star-forming gas contained a surprising amount of oxygen, and that the galaxy had advanced farther through chemical enrichment than researchers expected at that age. Another source of surprise came from the likely stellar mass. A galaxy cannot build 500 million solar masses of stars by forming only a few isolated clusters. It must process a large amount of gas. If star formation began 100 million years before the observed moment, the average rate required to build that mass would be several solar masses per year, even before accounting for mass return to the gas by dying stars. The real history was probably not constant. Webb modelling favoured a strong recent burst during the final few million years before observation. Other theoretical reconstructions have proposed earlier episodes of star formation, dusty phases, feedback-driven outflows, and later clearing of the dust. Different models can reproduce parts of the data, but they agree that a quiet, slowly developing system is not sufficient. bursty activity helps explain brightness. During a fresh burst, numerous massive stars form almost together. They produce intense ultraviolet radiation and strongly ionize the surrounding gas. The galaxy becomes much easier to detect. After several million years, those stars begin to die and the ultraviolet luminosity falls. A survey is more likely to find the galaxy during the bright phase than during a quiet one. Bursts also accelerate chemical enrichment, but they create another problem. The same massive stars that manufacture oxygen release enough energy to disturb the gas. An efficient early galaxy must form stars rapidly, while preventing feedback from shutting the process down completely. It may do this by sitting in a more massive dark matter halo than expected, by receiving a steady supply of fresh gas, or by allowing expelled material to return. Gas inflow can dilute the metallicity by adding relatively pristine hydrogen and helium. Outflows can lower the metallicity by carrying enriched material away. Continued star formation raises it by producing new elements. The observed abundance reflects the result of all three processes. A high metallicity at an early time may indicate strong production, effective retention, reduced dilution, or some combination of them. A large surrounding reservoir of neutral gas would add another complication. If fresh, metal-poor gas were constantly entering the central region, it should dilute the oxygen abundance unless enrichment proceeded very quickly. The galaxy may therefore have been producing metals at a substantial rate, while also gathering material from its surroundings. The type of stars that formed could influence that rate. Astronomers describe the distribution of stellar masses with the initial mass function. In the nearby universe, low-mass stars are much more common than very massive ones. Low-mass stars contribute greatly to the total stellar mass, but relatively little to immediate ultraviolet light and rapid oxygen production. An early stellar population containing a larger proportion of massive stars would produce more ultraviolet radiation, more ionizing photons, and more oxygen for each unit of total stellar mass. Such a top-heavy distribution is one possible explanation for bright enriched early galaxies. It is not yet established as the answer. Stellar populations at redshift 14 cannot be counted one star at a time, so the mass distribution must be inferred indirectly. Binary stars may also matter. Interactions between two stars can strip their outer layers, extend the production of ionizing radiation, and change which elements are released. Rapid rotation can mix material inside a star and alter its evolution. The first chemically enriched stellar populations may not behave exactly like the isolated, slowly rotating stars used in the simplest models. None of these possibilities removes the time constraint. They offer ways to use the available time more efficiently. A larger proportion of massive stars shortens the enrichment schedule. Bursty star formation concentrates activity. Efficient gas inflow supplies fuel. A deep, dark matter halo helps retain material. Low dust attenuation allows the resulting ultraviolet light to escape. JADES-GS-Z-14- may have benefited from several favourable conditions at once. Selection effects must also be remembered. Astronomers are more likely to discover an unusually bright galaxy than a typical faint one at redshift 14. JADES-GS-Z14- may represent the fast-growing edge of the population rather than the average early galaxy. Comparing it with a typical model galaxy can therefore exaggerate the mismatch, unless the model also accounts for rare objects. The discovery remains important even under that interpretation. A rare galaxy must still be physically possible within the available cosmic volume. Models must produce not only average systems but also the most extreme ones at approximately the right frequency. Webb's result that luminous galaxies appear more common than pre-Webb extrapolation suggested makes it harder to treat every bright source as an isolated exception. Chemical enrichment provides a particularly valuable test because brightness alone can be altered by several effects. A brief burst, low dust, gravitational lensing, or a hidden black hole can make a galaxy appear more luminous, without requiring a proportionate increase in its total stellar mass. Oxygen cannot be produced merely by removing dust from the line of sight. It requires nuclear reactions inside stars. The ALMA line therefore confirmed that significant stellar processing had occurred, even if the stellar mass estimate changed, even if the recent star formation rate were revised, and even if part of the ultraviolet light had an unexpected origin, the oxygen would still require an earlier population of stars. Researchers were also surprised by how clearly ALMA detected the line. Previous searches for far-infrared emission from secure galaxies beyond redshift 10 had often failed to find a strong feature. One concern was that very early galaxies might be too metal-poor, too faint, or too affected by their surrounding conditions for short observations to succeed. JADES-GS-Z14-0 produced a 6.6 sigma detection in less than 3 hours of integration per frequency setting, demonstrating that at least some galaxies at this distance can be studied in much greater physical detail than expected. The absence of detected dust continuum added an interesting contrast. The galaxy showed substantial oxygen enrichment but very little measurable dust emission. Oxygen can be dispersed quickly by massive stars, while dust production and survival depend on additional processes. Supernovae can form dust, but their shocks can also destroy it. Young galaxies may therefore become enriched with gaseous heavy elements before building a large stable dust supply. A strong oxygen line, weak carbon line, high ionization, and little dust describe a harsh interstellar environment. The stars were producing energetic radiation, the gas was being processed rapidly, and feedback may have removed or rearranged part of the material. Chemical maturity in this case did not mean calmness. It meant that the galaxy had already experienced enough stellar activity to move beyond a primordial composition. The adolescent comparison works because development is being judged by evidence of earlier activity. A baby galaxy would mainly contain its original hydrogen and helium, with few traces of completed stellar lives. JADES-GS-Z14-0 already carried the products of stars that had formed and died. It also contained a new population continuing the process. Unlike a human adolescent, however, a galaxy has no standard timetable. There is no fixed age at which it must reach a certain metallicity or stellar mass. The expectation comes from physical models and observations of other systems. When a galaxy develops faster than predicted, scientists do not conclude that it has broken a cosmic rule. They examine which assumptions made the predicted schedule too slow. Perhaps star formation began earlier than the models assumed. Perhaps the first halos collected gas with greater efficiency. Feedback may have been less effective at stopping growth in certain dense systems. Stellar populations may have generated more light and oxygen per unit mass. Metal-rich outflows may have remained close enough to return. The fraction of galaxies caught during bright bursts may also be larger than expected. Answering those questions requires finding more galaxies from the same period. One object cannot reveal whether early enrichment was common, rare, or limited to unusually massive halos. ALMA observations of additional Webb-selected galaxies can search for oxygen and carbon lines. Deep Webb spectroscopy can measure other elements and constrain star formation histories. Comparisons between detections and non-detections will show whether JADES-GS-Z14-0 is an early example of a broad population or a particularly efficient exception. The immediate evidence already requires a sequence of fast events. Primitive gas gathered inside a growing halo. Dense regions collapsed. Massive stars formed in large numbers. Their cores converted lighter nuclei into oxygen. Winds or explosions released the new material. The gas became mixed and ionized. More stars formed strongly enough for the galaxy to remain ultraviolet bright when the observed light departed. Every stage occurred under conditions that differed from those in the modern Milky Way. The gas contained fewer cooling elements. The cosmic microwave background was warmer. Galaxies were smaller and denser. Accretion from the surrounding universe was more rapid. Stellar feedback acted on shallow gravitational systems. A successful explanation must account for all of these conditions rather than simply speeding up a present-day galaxy. The oxygen line has narrowed the problem. Astronomers no longer need to ask only whether early galaxies could produce heavy elements. They must determine how JADES-GS-Z14-0 produced enough oxygen, retained or recycled it, and continued forming stars within a few 100 million years. Deep inside the earliest massive stars, oxygen began as helium and carbon. Gravity supplied the pressure, nuclear reactions supplied the heat, and the star's mass determined how quickly the process moved. There was no oxygen waiting in the original gas cloud. Every oxygen nucleus had to be assembled after the star formed. The first stellar populations began with almost pure hydrogen and helium. Astronomers call truly metal-free stars population 3 stars. Their exact range of masses remains uncertain because no confirmed individual population 3 star has been studied directly. Numerical simulations do not support one simple picture in which every first star had the same enormous mass. Depending on the cloud, accretion rate, fragmentation, and radiative feedback, simulations have produced stars ranging from a few solar masses to several hundred solar masses, with many models favouring masses of several tens of suns or more. Some primordial clouds may have formed one dominant star, while others produced binaries or small multiple systems. This uncertainty matters because stellar mass controls nearly every part of oxygen production. A star with 15 times the Sun's mass follows a different life from one with 60 solar masses. A star above 100 solar masses may encounter physical instabilities that never occur in a smaller star. Some stars explode and eject much of their oxygen. Others collapse into black holes and keep a large fraction of their newly formed elements trapped inside. Metal-free stars also differed from modern stars before fusion even began. The clouds that formed them lacked carbon, oxygen, silicon, and dust. Those ingredients help present-day gas radiate energy and break into smaller fragments. Primordial gas cooled mainly through molecular hydrogen and a limited set of atomic processes. It generally remained warmer during collapse, which encouraged larger fragments and higher accretion rates. That tendency helped the first protostars grow rapidly, although fragmentation could still divide the available gas among several objects. A forming star grows by pulling in gas from the disk and cloud around it. As material falls inward, gravity compresses the central region. The temperature rises until the core becomes hot enough for hydrogen fusion. Once that happens, the young object becomes a true star rather than a protostar still relying mainly on gravitational contraction. The first energy-producing reactions turned hydrogen nuclei into helium. At the beginning, a completely metal-free star could not rely on the carbon-nitrogen-oxygen cycle in the same way that many modern massive stars do, because there was no carbon, nitrogen, or oxygen available to act within that chain. Hydrogen fusion could begin through reactions that do not require those elements. The core then became hot enough for a small amount of helium to form carbon through the triple alpha reaction. Once trace carbon existed, the CNO cycle could operate and become an efficient source of energy in a massive star. The details sound circular at first. A massive star normally uses carbon to help fuse hydrogen, but the first massive stars began without carbon. The solution was a hotter core. The star contracted until alternative reactions produced enough energy and eventually enough carbon for the faster CNO process to take over. Metal-free stars were therefore expected to be hotter and more compact in several phases of their evolution than otherwise similar stars that began with heavier elements. Hydrogen burning occupies most of a star's lifetime, but a massive star uses its fuel quickly. Greater mass creates stronger gravity, which raises the pressure and temperature in the core. The higher temperature makes nuclear reactions proceed much faster. A star with dozens of solar masses contains more hydrogen than the Sun, but it consumes that hydrogen so aggressively that its life may last only a few million years. This is the first reason early enrichment was possible. JADES-GS-Z14-0 did not need to wait billions of years for Sun-like stars to age. Its most massive stars could form, burn their central hydrogen, produce oxygen, and die within a small fraction of the galaxy's available time. The timetable was tight, but massive stars are not known for pacing themselves. When hydrogen in the central region becomes depleted, the outward pressure from core hydrogen fusion weakens. Gravity compresses the helium-rich core, raising its temperature. Hydrogen can continue burning in a shell outside the core, while the center moves toward helium fusion. Helium nuclei are more difficult to combine than hydrogen nuclei because they carry greater positive charge. The core must reach a much higher temperature. Once the conditions become sufficient, 2 helium-4 nuclei can briefly form beryllium-8. That nucleus is unstable and normally falls apart almost immediately. In a dense stellar core, however, a third helium nucleus can sometimes arrive before the beryllium decays. The 3 helium nuclei then form carbon-12. This is the triple alpha process. The word alpha refers to a helium-4 nucleus, containing 2 protons and 2 neutrons. 3 such nuclei contain 6 protons and 6 neutrons, which produces carbon-12. The process supplies the first large amounts of carbon inside the star. Oxygen follows when a carbon-12 nucleus captures another helium-4 nucleus. The resulting oxygen-16 nucleus contains 8 protons and 8 neutrons. The reaction releases energy in the form of radiation. It is written by nuclear physicists as carbon-12 plus helium-4, producing oxygen-16 and a gamma-ray photon. The competition between the triple alpha process and carbon's capture of helium helps determine how much carbon and oxygen remain after core helium burning. If carbon captures helium efficiently, more oxygen is produced. If the reaction proceeds less efficiently, more carbon survives. The exact rate remains important in stellar modelling because relatively small differences can alter the later structure and final fate of a massive star. Neither carbon nor oxygen is distributed evenly through the star. They form mainly in the hot core during helium burning. Convection and other mixing processes can move material within the stellar interior. Rotation may stir additional material between layers. Binary interaction can strip out a gas, alter the core mass, or expose regions containing products of nuclear burning. After central helium becomes scarce, a sufficiently massive star continues through further stages. Carbon burning produces elements including neon, sodium, and magnesium. Neon burning can contribute oxygen and magnesium. Oxygen burning then produces silicon, sulfur, and related elements. Silicon burning eventually builds nuclei near the ion group. Each later stage takes less time than the one before it. Hydrogen burning may last millions of years. Helium burning lasts much less. Carbon, neon, oxygen, and silicon burning proceed on progressively shorter schedules, with the final stages sometimes lasting days or less in the most massive stars. The star develops layers of different composition, often compared with an onion. Hydrogen remains farther out, followed by helium, carbon, oxygen, silicon, and an iron-rich center. The comparison is useful as long as we do not imagine perfectly neat layers. Real stars rotate, mix, pulse, lose mass, and may exchange material with companions. The boundaries can be complicated. Still, the broad structure explains why oxygen can be abundant inside a massive star before the final collapse. It occupies large regions outside the innermost iron-rich core. Iron presents a problem because fusing iron group nuclei does not release energy in the way earlier fusion stages do. Once a massive star develops an iron core that can no longer support itself, the center collapses. Electrons are driven into protons, producing neutrons and neutrinos. The core reaches nuclear densities, and the collapse is halted abruptly. A shock forms and begins moving outward. Producing a successful core collapse supernova is not as simple as allowing that first shock to travel directly out of the star. The shock loses energy while breaking apart heavy nuclei and moving through dense material. Neutrinos released by the forming neutron star may deposit enough energy behind it to help revive the explosion. Convection, turbulence, rotation, and asymmetries also affect the outcome. Modern simulations still study exactly which stars explode successfully and which collapse into black holes. When the explosion succeeds, the outward-moving shock passes through oxygen-rich layers and ejects them into space. Some oxygen was created during the star's earlier helium burning. Additional nuclear processing can occur as the shock heats the material. The supernova sends the resulting elements into the surrounding gas at thousands of kilometers per second. The ejected oxygen does not leave as one tidy cloud labelled for future astronomers. It mixes with hydrogen, helium, carbon, silicon, iron, and other products from the star. The proportions depend on the star's initial mass, internal mixing, rotation, explosion energy, and the amount of material that falls back onto the compact remnant. Fallback can reduce the quantity of oxygen that escapes. Material may initially move outward, but fail to reach sufficient speed. Gravity pulls it back toward the neutron star or black hole. In a weak explosion, much of the inner stellar material can disappear into the remnant. Some massive stars may fail to produce a bright supernova at all. Their cores collapse, a black hole forms, and only a limited amount of material escapes. This outcome is important for early chemical enrichment, because making oxygen inside a star does not help the galaxy if the oxygen never leaves. Chemical evolution studies show that the fraction of high-mass stars that eject their oxygen has a major effect on the eventual abundance in galactic gas. A black hole-forming star is not always chemically useless. Winds, pulsations, rotation, or binary stripping may remove material before the final collapse. A weak or asymmetric explosion may eject outer oxygen-rich layers, while much of the inner material falls back. Models of metal-free supernovae have produced carbon and oxygen-rich ejecta, with relatively little iron when strong fallback traps the deeper layers. Such explosions have been investigated as possible sources of the chemical patterns observed in some extremely metal-poor stars. Very massive stars introduce another possible route. Under certain conditions, an extremely hot core begins converting energetic gamma-ray photons into electron-positron pairs. Radiation pressure had been helping support the star, and this conversion reduces that support. The core contracts, heats rapidly, and can ignite oxygen explosively. For a certain range of core masses, the resulting nuclear energy can reverse the collapse and disrupt the entire star. This is a pair instability supernova. Unlike an ordinary core collapse event, it may leave no neutron star or black hole. The whole star can be dispersed, releasing large quantities of oxygen, silicon, and other elements into the surrounding environment. Classic non-rotating models place full pair instability explosions in primordial stars with initial masses of roughly 140 to 260 solar masses, although mass loss, rotation, and updated stellar physics can shift the boundaries. Stars in a somewhat lower range may undergo pulsational pair instability, ejecting material through repeated violent pulses before the remaining core eventually collapses. Above the full pair instability range, the star may collapse into a black hole without ejecting most of its heavy elements. Pair instability supernovae are efficient distributors because they can unbind the entire star. Their theoretical yields can contain enormous masses of oxygen. They also create a distinctive chemical pattern, with relatively strong production of elements containing even numbers of protons and weaker production of neighbouring odd-numbered elements. Researchers look for this pattern in very old stars and primitive gas as evidence that pair instability events contributed to the first enrichment. The available evidence does not show that pair instability supernovae were the main source of oxygen in JADES-GS-Z. 14-0. Simulations predict that stars capable of these explosions can form, but their frequency depends on the uncertain mass distribution of population 3 stars. Chemical patterns in extremely metal-poor stars have often been interpreted as favouring contributions from more ordinary core collapse or black hole-forming supernovae rather than a universe dominated by pair instability events. A realistic early galaxy probably received oxygen from several kinds of stars. Some stars may have exploded as core collapse supernovae. A smaller number may have undergone pair instability. Others may have collapsed into black holes after losing part of their outer layers. Binary systems could have changed the outcome by transferring mass or merging. Rotation is particularly important in metal-poor stars. A rotating star can mix hydrogen-burning and helium-burning products between regions that would otherwise remain more separate. This mixing changes the amounts of carbon, nitrogen, and oxygen produced. Rotation also affects the size of the final core and may influence whether the star explodes, pulses, or collapses. Mass loss behaves differently at very low metallicity. In modern massive stars, heavy elements absorb radiation and help drive strong stellar winds. A metal-free star lacks those elements at its surface, so the usual line-driven winds may be weaker. The star can therefore retain more of its mass until late in its life. That can produce a larger helium and oxygen core, but it can also make direct black hole formation more likely. Binary companions provide alternative ways to remove material. One star can expand and transfer gas to the other. A shared envelope can strip away hydrogen-rich outer layers. 2 stars may merge and create a more massive object with a different internal structure. These possibilities make oxygen yields difficult to calculate from initial mass alone. The earliest enrichment also changed the stars that formed afterward. Once a supernova added carbon, oxygen, and other heavy elements to a gas cloud, the gas gained new ways to cool. Carbon and oxygen ions can emit radiation through fine structure transitions. Dust grains, if present, can cool very dense gas and encourage fragmentation. The next generation could therefore form with a wider range of masses, including longer-lived low-mass stars. Astronomers call these enriched successors population 2 stars. They were still extremely metal-poor by modern standards, but they were not chemically pristine. Their initial gas already contained the products of earlier stellar lives. Population 2 stars could then manufacture and release additional oxygen, building enrichment in repeated steps. Only a small amount of heavy material is needed to change the cooling behavior of primordial gas. One energetic supernova can enrich a nearby region above the level at which later star formation begins to differ from the original population 3 mode. The effect is local, however. A supernova may enrich one cloud while leaving another almost untouched. The transition from population 3 to population 2 did not happen everywhere on one date. Simulations of the first galaxies show this uneven pattern clearly. A primordial supernova can spread metals through a growing halo, but radiative feedback and gas motion create a complicated distribution. Some dense regions become enriched enough to form population 2 stars, while nearby mini-halos remain chemically primitive. Turbulent mixing can eventually make the central gas more uniform, but that takes time and depends on the galaxy's assembly history. JADES-GS-Z14-. O may therefore have contained several chemical environments at once. The compact region producing the bright O3 line had already received oxygen and was exposed to energetic ultraviolet radiation. Farther out, neutral gas may have remained much less enriched. Newly arriving material from the surrounding cosmic web could have contained mostly hydrogen and helium. The oxygen seen by ALMA probably did not come from the galaxy's very first stars alone. Population 3 stars could have supplied the initial enrichment, but later metal-poor population 2 stars were likely contributing as well. Once the first oxygen and carbon changed the cooling conditions, star formation could proceed in denser clusters and through additional generations. Those later massive stars still produced oxygen quickly. A star does not need to be completely metal-free to have a short lifetime. a 20 or 40 solar mass population 2 star can reach core collapse within several million years. If JADES-GS-Z14-0 had been forming stars for close to 100 million years before the observed moment, many cycles of massive star birth and death could overlap. The word generation can be misleading because galaxies do not stop all star formation, wait for every star to die, mix the material perfectly and then begin again. One cluster may form while supernovae from another are already expanding. A metal-enriched shell can collapse and make new stars while more primitive gas is still arriving elsewhere. Several populations can coexist, with no cosmic official available to stamp the paperwork. Rapid star formation increases oxygen production, but it also increases the energy released into the gas. Every additional group of massive stars contributes radiation, winds, and explosions. Those effects can drive oxygen out of the galaxy. A system that enriches itself quickly must either retain much of the ejecta, replace lost gas, or produce metals faster than they escape. The amount of oxygen measured in JADES-GS-Z14-0 remains model dependent. The original ALMA analysis, combined with Webb photometry and ionized gas models, suggested a metallicity of about 5 to 20% of the solar value. Later, deep Webb spectroscopy directly detected rest frame optical oxygen lines and found a gas phase oxygen abundance around 10% of solar using standard strong-line diagnostics, though detailed modelling allowed a higher value and showed that substantial uncertainty remains. Whichever value proves most accurate, the basic requirement is unchanged. A significant population of massive stars had to form before the light left JADES-GS-Z14-0. Some of those stars completed helium burning and created oxygen. Enough of them released the oxygen instead of locking it into black holes. The ejecta entered ionized gas and remained concentrated enough to produce the line that ALMA detected. One pair instability supernova could eject a great deal of oxygen, but a single event would not automatically explain the whole observation. The oxygen had to mix into an active star-forming environment, and the galaxy's ultraviolet luminosity indicated a substantial living stellar population. Repeated core collapse supernovae from a broader mass range may provide a more natural route, possibly with occasional contributions from more extreme explosions. The relative amounts of carbon, oxygen, nitrogen, and iron can eventually help separate these possibilities. Different stellar masses and explosion types produce different abundance ratios. Pair instability events leave one pattern, fallback supernovae leave another. Rotating metal-poor stars can increase nitrogen and alter carbon to oxygen ratios. Deep spectra of JADES-GS-Z14-0 and other early galaxies may therefore reveal not only that heavy elements existed, but which stars most likely produced them. ALMA's oxygen line supplies one part of this chemical record. Webb's ultraviolet, visible and infrared measurements supply others. No single feature can reconstruct the exact mass distribution of the first stars, but several elemental ratios can reduce the range of viable histories. The stellar furnaces themselves were fast enough to operate within the available time. Massive stars can produce oxygen in a few million years. Their supernovae can spread it shortly afterward. The harder problem is one of quantity and repetition. JADES-GS-Z14-0 needed enough massive stars, enough successful ejection, enough mixing, and enough continued star formation to reach its observed state before the universe was 300 million years old. Stellar physics explains where the oxygen came from. It does not by itself explain how the galaxy organized the process so efficiently. The remaining question concerns the system around those stars. A star does not explode, distribute its oxygen evenly through a galaxy, and leave the system ready for the next generation. The process depends on how gas enters the galaxy, how quickly stars form, which stars are born, how they die, where their ejecta travel, and whether fresh hydrogen and helium dilute the enriched material afterward. JADES-GS-Z-14-O had to manage all of those steps while the universe was still less than 300 million years old. The simplest description begins with gas falling into a dark matter halo. Dark matter supplied most of the gravity, while ordinary gas provided the material that could cool and form stars. At redshift 14, matter was denser on average than it is today, and gas could arrive rapidly along the growing structure sometimes called the cosmic web. A strong supply of gas helps a galaxy build stars, but an inflow of nearly pristine material also lowers the average metallicity. The galaxy therefore had to enrich its gas faster than incoming hydrogen, and helium could dilute it. Astronomers often represent this competition with a basic reservoir model. Gas enters, some become stars, massive stars return part of their material, including newly made oxygen. Outflows remove gas, while later inflows replenish it. The metallicity at any moment depends on the balance among production, retention, loss, and dilution. Nothing in that balance requires a galaxy to develop slowly, but rapid enrichment demands unusually effective production, or unusually favourable retention. Webb's original modelling indicated a stellar mass around 400 million solar masses, with a 10 million year average star formation rate close to 19 solar masses per year. The resulting specific star formation rate was very high, meaning the galaxy was adding stars quickly compared with the mass it had already assembled. The precise values remained sensitive to assumptions about dust, metallicity, stellar populations, and star formation history, but every reasonable fit describes a system undergoing vigorous early growth. One way to build the observed mass is to form stars at a moderate rate for a long fraction of the galaxy's life. Another is to alternate between quiet intervals and short, intense bursts. Early galaxies are expected to favour the second pattern because stellar feedback can repeatedly heat or expel gas. Material gathers, a burst begins, massive stars appear, and their radiation and explosions interfere with the next round. After the gas cools, returns, or is replaced by fresh inflow, star formation resumes. Burst can enrich gas quickly. A large group of massive stars forms within a short interval, and some of those stars release oxygen only a few million years later. The same burst also produces intense ultraviolet radiation, explaining why a galaxy may become unusually bright for a limited period. A survey is much more likely to detect the system during that luminous phase than while it is recovering from feedback. MIRI observations of JADES-GS-Z14-0 supported the presence of a strong recent burst. The preferred modelling in that study placed roughly 500 million solar masses in stars and found that at least 1/3 of the measured 7.7 micrometer flux probably came from strong hydrogen and oxygen emission lines. Those lines require an active population of young hot stars and ionized gas that has already been enriched. A theoretical reconstruction published before the Army oxygen announcement proposed an especially eventful history. In that model, star formation began at a redshift near 26.7. Early activity was faint and bursty because feedback repeatedly regulated it. Dust later shielded the gas, allowing a heavily obscured phase in which about 70% of the model's final stellar mass formed during roughly 20% of its star-forming lifetime. A radiation-driven outflow then cleared much of the dust and reduced the star formation rate from about 100 to 15 solar masses per year before the observed moment. This is one possible history rather than a uniquely established biography, but it demonstrates how a galaxy can build mass rapidly without remaining equally bright at every stage. Dust shielding may sound surprising in a galaxy this young. Dust must also be manufactured from heavy elements, and ALMA did not detect a strong dust continuum from JADES-GS-Z14-0. A brief earlier dusty period is nevertheless possible if supernovae produce grains rapidly and later feedback destroyed or expelled much of them. The absence of detectable dust at the observed time does not prove that the galaxy had never contained more dust before. Star formation efficiency is central to the problem. The term describes how much available gas becomes stars over a given interval. In nearby molecular clouds, only a small fraction of the gas turns into stars before feedback disperses the cloud. A young galaxy with a dense gas supply might reach higher efficiencies in its compact central regions. Even a modest increase would allow it to build stellar mass and heavy elements sooner than many pre-Webb models predicted. Efficiency cannot rise without limit. Turning gas into stars too rapidly creates more radiation, winds, and supernovae, which can shut down the process. A model that solves the brightness problem by making star formation nearly perfect may create a feedback problem instead. The most plausible histories allow rapid conversion in selected dense regions, while outflows and replenishment regulate the galaxy as a whole. The stellar mass distribution introduces another uncertainty. If the early galaxy produced a larger fraction of high-mass stars than the Milky Way does today, it would generate more ultraviolet light and more oxygen for each unit of total stellar mass. Massive stars complete their lives quickly and dominate oxygen production. A top-heavy initial mass function could therefore reduce the amount of star formation needed to explain both the brightness and the enrichment. Current observations do not directly measure that mass distribution. Individual stars cannot be separated at this distance, and several combinations of age, dust, metallicity, binary evolution, and stellar mass can reproduce similar integrated light. A top-heavy population is a possible part of the explanation, not a result already demonstrated by the oxygen line. Metal retention may be even more difficult than metal production. Supernova ejecta can leave a star at thousands of kilometers per second. JADES-GS-Z14-. O was compact, and its early gravitational potential may have been shallow compared with those of mature galaxies. Energetic outflows could remove much of the newly made oxygen before it mixed with the star-forming gas. A more massive dark matter halo would help. Stronger gravity could slow the ejecta, retain part of the hot gas, and allow material that moved outward to fall back later. This recycling process is often called a galactic fountain. The name sounds decorative, but the mechanism is practical. Gas rises out of the star-forming region, cools, and returns, carrying metals with it. In a very young galaxy, the fountain may be irregular and violent rather than resembling a steady circulation. Outflows do not need to remove every type of material equally. Hot, metal-rich gas can escape more easily than colder, denser clouds. Fresh gas may continue entering while enriched material leaves. The galaxy's central metallicity can rise even as its total supply is being exchanged. ALMA's O3 line traces ionized oxygen in a particular phase of the interstellar medium, not the average composition of all matter associated with the galaxy. This distinction helps reconcile apparently different observations. The original ALMA line analysis found a dynamical mass of about 1 billion solar masses, comparable to some estimates of the stellar mass. That comparison suggested a low gas fraction in the compact central region. The authors proposed that earlier radiation-driven outflows might have cleared gas and increased the fraction of ionizing photons able to escape. Later ALMA observations searched for the 158 micrometer line from singly ionized carbon and did not detect it. The resulting lower limit on the O3 to C2 ratio indicated extreme ionizing conditions and a young stellar population. Modelling in that study favoured a metallicity around 16% of solar, a relatively low gas density, and a gas fraction below roughly 77%. The authors again argued that strong feedback was probably influencing the galaxy's evolution. These quantities depend on interstellar medium models and line-to-gas conversions, so they should be treated as constraints rather than direct inventories. A non-detection of Verusi-2 can have several causes. The galaxy may contain little cold neutral gas in the region being measured. Its radiation field may be so intense that carbon is pushed into higher ionization states. Low density can reduce the efficiency of the line. Carbon may also be less abundant relative to oxygen, because the two elements are returned by different stellar populations on different schedules. Oxygen is produced efficiently by short-lived massive stars. A substantial fraction of carbon can also come from massive stars, but lower and intermediate mass stars contribute more carbon after longer delays. At an age below 300 million years, many of those slower stars would not yet have reached the ends of their lives. An early galaxy can therefore develop a high oxygen-to-carbon ratio, even when both elements are present. The same delay applies more strongly to iron from Type 1a supernovae. Core collapse supernovae from massive stars occur quickly and release oxygen and other alpha elements. Many Type 1a supernovae require binary systems to evolve for longer before exploding and supplying large quantities of iron. Young systems are therefore expected to contain more oxygen relative to iron than chemically older systems. Measuring several elemental ratios would reveal more of the enrichment schedule than oxygen alone can provide. Mixing adds another delay. A supernova can create oxygen during stellar evolution and eject it rapidly, but distributing that oxygen through a galaxy takes much longer. The expanding remnant interacts with surrounding gas, drives shocks, cools, fragments, and becomes part of turbulent flows. Some enriched pockets may reach a substantial metallicity, while nearby material remains close to its primordial composition. The metallicity inferred from bright emission lines is weighted toward the regions producing those lines. Hot stars illuminate nearby enriched gas, making it easier to detect than cold or neutral material. JADES-GS-Z14-0 could therefore contain a chemically advanced star-forming centre, surrounded by a much larger and less enriched reservoir. The measured oxygen abundance would then describe the active region rather than the entire halo. Evidence for a large neutral column appeared when researchers combined ALMA's precise redshift with Webb's Lyman break. The absorption could be explained by a damped Lyman alpha system containing a substantial amount of neutral hydrogen along the line of sight. That gas might lie within or around the galaxy. Its presence does not automatically contradict a low gas fraction inferred for the compact oxygen emitting region, because the methods may be probing different scales and phases. One measures motion and emission in the bright centre. The other measures absorption produced by neutral material in front of the ultraviolet source. Fresh neutral gas could help sustain later star formation, but it would also complicate the metallicity. If the reservoir were almost pristine, mixing it into the centre would lower the oxygen abundance. Maintaining a value near 10 or 20% of solar would require continued production, incomplete mixing, or in flow that arrived in a controlled way rather than immediately blending with every enriched cloud. The geometry of the system is largely unknown. JADES-GS-Z14- may contain several star-forming clumps. It may be interacting with smaller companions that are too faint to detect. Gas may enter along narrow streams rather than evenly from all directions. Outflows may escape through low-density channels while denser material remains. A single metallicity number compresses this three-dimensional structure into one convenient value. Recent spectroscopy has added a possible sign that outflowing enriched material extends beyond the main stellar light. A 2026 preprint reported strong C3 emission displaced by about 400 parsecs from the stellar continuum and interpreted the diffuse carbon-enriched region as evidence of an ongoing or past outflow. Under that interpretation, the estimated mass outflow rate was about 160 solar masses per year, several times the star formation rate. The result is recent and model dependent, but it supports a picture in which feedback moved enriched gas through the galaxy very efficiently. Such a large outflow would seem to work against rapid enrichment. If the galaxy expelled gas several times faster than it formed stars, why did so much oxygen remain visible? The answer may be that the observation catches only one part of a repeating cycle. Earlier starbursts could have produced a large oxygen supply. Some enriched gas escaped, some remained, and some may later return. The galaxy could continue receiving fresh material while losing another portion at the same time. Metallicity is therefore not a simple measure of how much total oxygen a galaxy has made. It is the amount of heavy elements relative to the gas in the region being studied. Removing hydrogen-rich gas can raise the measured metallicity even without producing new oxygen. Adding pristine gas can lower it even while the total oxygen mass stays constant. Outflows that preferentially remove metals have a different effect from outflows that sweep out a broad mixture. The estimated low central gas fraction, if confirmed, might partly explain why the measured metallicity became high so quickly. A fixed quantity of oxygen mixed into a smaller remaining gas reservoir produces a larger oxygen abundance. Feedback may have removed or consumed much of the central gas after an intense period of star formation, leaving an enriched region with less hydrogen available to dilute it. This possibility matches the idea of a post-starburst system. A galaxy can form most of its stars during a short obscured phase, then clear gas and dust through radiation pressure and supernovae. When observed afterward, it appears blue because little dust blocks the young stars, while its current star formation rate is lower than its earlier peak. The bright ultraviolet light does not necessarily show the moment of maximum stellar growth. There are important limits to this model. The inferred history relies on fitting a small number of measurements from an object that cannot be spatially resolved in fine detail. Different assumptions about the initial mass function, dust temperature, stellar ages, gas geometry, and escape of ionizing radiation can produce different solutions. No observation has recorded the galaxy continuously from its first star to the moment represented by the light we receive. Chemical evolution simulations must test many possible histories rather than reproduce one preferred narrative. A successful model should match the stellar mass, ultraviolet luminosity, size, oxygen line strength, carbon line limits, dust limit, neutral hydrogen absorption, and internal velocities at the same time. Improving one quantity while missing the others does not fully explain the galaxy. The rapid enrichment problem also depends on the oxygen yield assigned to massive stars. Stellar models disagree about how much oxygen escapes from stars of different masses, especially at very low metallicity. Rotation, binary interaction, explosion energy, and black hole fallback alter the result. If early massive stars released more oxygen than commonly assumed, the galaxy would need fewer stellar generations. If many collapsed quietly into black holes, the enrichment would be harder to achieve. The rate at which metals mix is equally uncertain. Some simulations assume efficient mixing within a region because they cannot resolve every turbulent motion. Real gas may remain chemically patchy. Strong oxygen emission from one enriched clump could then coexist with a much lower average metallicity across the galaxy. Better spatial resolution would help, although resolving structures only a few hundred light-years across at redshift 14 remains extremely demanding. JADES-GS-Z14-O may also be an extreme object selected precisely because it grew quickly. The most rapidly star-forming and least dust-obscured galaxies are easiest for Webb to find at these distances. A typical galaxy from the same time may be far fainter and more primitive. Rapid enrichment in one source does not prove that every galaxy developed at the same speed. The growing sample makes a purely exceptional explanation less comfortable. Webb has found more luminous galaxies beyond redshift 10 than several pre-launch forecasts predicted, and ALMA has begun detecting oxygen in other systems from the first few 100 million years. a 2025 study of JADES-GS-Z11-O, a less extreme galaxy seen about 400 million years after the Big Bang, reported oxygen enrichment around 30% of solar in a system undergoing strong starbursts. That result suggests that early oxygen enrichment may not be confined only to the brightest known object, although the sample is still small. The mystery is therefore becoming a population question. Astronomers need to know how often early halos formed stars efficiently, how commonly they retained metals, and how strongly dust affected which galaxies surveys detected. They also need to separate short luminous phases from sustained growth. A galaxy observed during a 5 million year burst should not be interpreted in the same way as one that maintained the same star formation rate for 100 million years. More ALMA observations can measure O3, C2, and dust in a wider sample. Webb can provide ultraviolet and optical lines, stellar continua, and constraints on ages and ionization. Together, the instruments can test whether oxygen abundance correlates with stellar mass, size, star formation rate, or the strength of outflows. Theoretical models will then have to reproduce the distribution rather than one object. They must create ordinary faint galaxies, rare luminous galaxies, metal-poor systems, and unexpectedly enriched ones in the correct proportions. This is more demanding than adjusting one parameter until JADES-GS-Z14-O looks plausible. For the moment, no single mechanism explains every observation without uncertainty. Rapid early star formation probably produced a large population of massive stars. Their short lives supplied oxygen quickly. Compact conditions may have raised the star formation efficiency. A relatively massive halo may have retained or recycled part of the ejector. Bursts and outflows changed the gas supply, while low dust attenuation allowed ultraviolet light to escape. Incomplete mixing may have made the oxygen-bright regions more enriched than the galaxy as a whole. These processes are individually familiar. Their timing and combined efficiency are what make JADES-GS-Z14-O unusual. The galaxy appears to have gathered gas, built stars, manufactured oxygen, expelled material and continued shining strongly before many older models expected a system of this size to exist. Changing a model of the early universe does not usually begin with someone erasing a blackboard and announcing that everything before lunch was wrong. More often, several observations begin refusing to fit comfortably inside the same picture. One galaxy appears too bright, another seems too massive, a third contains chemical elements sooner than expected. Each result can be explained individually, but as the number grows, astronomers have to ask whether the assumptions connecting the observations to the theory need to change. JADES-GS-Z14-0 belongs to that growing group. Before the James Webb Space Telescope began science operations, astronomers already expected galaxies to exist during the first few 100 million years after the Big Bang. Simulations produced them. Hubble had found galaxies from surprisingly early periods, and theoretical models described how dark matter structures should gather gas and begin forming stars. The basic idea of early galaxy formation was not in doubt. What was uncertain was how quickly those galaxies would become large, bright, chemically enriched, and easy enough for us to detect. Many pre-Webb forecasts predicted a rapid decline in the number of luminous galaxies as observations approached redshifts above 10. There should still be galaxies there, but the brightest systems were expected to become increasingly rare. That expectation followed naturally from the limited time available. Dark matter halos had only recently begun assembling. Gas was still settling into them. The first stellar populations were turning on. Supernova feedback could remove gas from small systems. Heavy elements and dust had barely begun to accumulate. Then Webb started finding more bright galaxies than many of those predictions suggested. Some early candidates turned out to require more cautious interpretation, as always happens when a new telescope enters unexplored territory. Photometric estimates can mistake a lower redshift object for a very distant one. Strong emission lines can alter broadband colours. Dust can create confusing spectral shapes. Gravitational lensing can make a source appear brighter than it really is. Spectroscopy gradually removed many of those uncertainties. JADES-GS-Z14- survived the process. It was not simply a red object whose distance had been overestimated. Webb spectroscopy confirmed that it belonged near redshift 14. ALMA then fixed the value at about 14.179 with extraordinary precision by detecting the oxygen line. At the time of the ALMA result, the galaxy represented a view of the universe roughly 290 million years after the Big Bang. Its brightness was already difficult to fit into some earlier expectations. Its chemical state made the problem more specific. Brightness alone can sometimes be deceptive. A galaxy can look unusually bright because it happens to be observed during a short starburst. A small amount of dust can make a large difference to the ultraviolet radiation that escapes. A central black hole can add light. Gravitational lensing can amplify the source. A stellar population containing more massive stars can produce more ultraviolet radiation without requiring proportionally more total stellar mass. Oxygen is harder to explain away. An oxygen atom requires a previous sequence of nuclear reactions inside a star. Significant oxygen in a galaxy means that stars have already formed, evolved far enough to produce the element, and returned some of it to the surrounding gas. The enriched material then has to remain available long enough to be observed. Brightness tells astronomers that a galaxy is active. Oxygen tells them that something important happened before the light they are seeing now. This is why the ALMA result adds a chemical clock to the story of cosmic dawn. The clock does not provide one exact date for the formation of the first stars. Chemical enrichment is too complicated for that. The amount of oxygen produced depends on stellar masses, rotation, binary interactions, explosion energies, and the fraction of material lost into black holes. The observed abundance also depends on gas inflow, outflow, mixing, and ionization. Even with those uncertainties, the galaxy cannot begin its history at the moment we observe it. Earlier star formation is required. If JADES-GS-Z14-0 had simply switched on a few million years before the observed light left, it might produce plenty of ultraviolet radiation from newborn massive stars. It would have a much harder time explaining significant enrichment throughout the oxygen-emitting gas. Some stars had to come first. That pushes the onset of meaningful star formation farther back. The first stars in the universe may have begun appearing around 100 million years after the Big Bang, although there is no single agreed birthday for the first star. Different regions collapsed at different times. In an unusually dense region, star formation could start earlier than average. JADES-GS-Z14-0 may have developed in exactly such an environment. An early start solves part of the problem. It does not solve all of it. Once the first stars form, the galaxy must keep enough gas available for further growth. Massive stars live quickly and return oxygen within a few million years, which helps. Their supernovae also heat the gas and can push it away, which does not help nearly as much. The same stars that accelerate chemical enrichment can interfere with the next round of star formation. This conflict is one reason feedback plays such a large role in galaxy simulations. A model that allows gas to collapse too efficiently may create galaxies that become too massive too soon. A model with feedback that is too strong may prevent galaxies like JADES-GS-Z14-0 from forming at all. Researchers have to reproduce both the growth and the regulation. Webb's early galaxy population suggests that this balance may differ from what many pre-launch models assumed. One possibility is that star formation was more efficient in some early dark matter halos. Dense gas at high redshift may have converted into stars rapidly. A higher efficiency would allow a galaxy to build stellar mass sooner and produce more massive stars capable of enriching the gas. That explanation has limits. If efficiency becomes extremely high, the resulting radiation and supernova activity should drive powerful feedback. The galaxy cannot simply convert every arriving cloud into stars without consequences. A second possibility is burstiness. Instead of forming stars at a steady rate, a galaxy may alternate between intense activity and quieter periods. During a burst, it becomes much brighter and produces many massive stars at once. Several million years later, those stars begin returning oxygen. Feedback then reduces star formation until fresh gas arrives or previously expelled material falls back. This kind of history can make an early galaxy appear surprisingly bright without requiring it to maintain that brightness continuously for hundreds of millions of years. A third possibility involves dust. Dust absorbs ultraviolet light. Two galaxies with the same underlying stellar population can therefore look very different if one contains enough dust to hide its younger stars. Very early galaxies may contain less surviving dust than expected, either because they have not had time to make much of it, or because intense radiation and supernova shocks destroy and remove it. JADES-GS-Z14-O has shown little evidence for a large dust reservoir. ALMA did not detect its dust continuum in the observations that revealed oxygen. The upper limit on its dust-to-stellar mass ratio was very low. Less dust allows more ultraviolet light to escape, helping explain why some early galaxies look extremely luminous. That does not explain the oxygen abundance by itself. In fact, low dust combined with significant oxygen creates another interesting question. Both dust and oxygen require stellar processing, yet the galaxy appears rich enough in gaseous heavy elements to produce strong oxygen emission without having accumulated a large visible dust supply. Supernovae may create dust quickly, but supernova shocks can also destroy it. Outflows may preferentially remove small grains. The intense radiation field can change the structure of the interstellar medium. Early galaxies may therefore pass through chemical states that are uncommon in nearby galaxies. Carbon provides another clue. ALMA observations looking for the 158 micrometer C2 line in JADES-GS-Z14-0 did not produce a detection. Combined with the strong O3 line, this gives a high O3 to C2 ratio. Models interpret the ratio as evidence for highly ionized conditions in a young stellar population. The same analysis found a metallicity around 16% of solar, consistent with rapid enrichment, while also suggesting a relatively low gas density and limited cold gas content in the region being probed. This does not necessarily mean the entire galaxy lacks gas. Different observations trace different phases. Ionized oxygen tells us about gas strongly affected by young stars. Neutral hydrogen absorption can reveal gas farther out. Carbon lines may trace cooler or differently ionized regions. Dust emission measures another component. A young galaxy can contain all of these environments at the same time. The increasingly complicated picture is actually useful. Early galaxies may not be scaled-down versions of the Milky Way. Their interstellar media can be extremely uneven, with strong radiation fields, rapid inflow, strong outflow, and chemically enriched pockets sitting beside more primitive gas. That possibility changes how astronomers interpret metallicity measurements. When we say that JADES-GS-Z14- may have had an oxygen abundance around 10 or 20% of the Sun's value, we are not necessarily describing every atom associated with the galaxy. We are describing the gas that produces the measured emission under a particular physical model. Later Webb observations have strengthened the evidence that the system was genuinely enriched. Ultra-deep MIRI spectroscopy, reported in late 2025, detected the rest frame optical O3 lines at roughly 11 sigma significance and H-alpha at about 4 sigma. The observations indicated low dust attenuation and a recent star formation rate of about 10 solar masses per year. Standard strong-line methods gave an oxygen abundance around 10% of solar, although detailed photoionization modelling allowed a substantially higher value, with a preferred solution around half solar and large uncertainty. The researchers concluded that existing simulations had difficulty reproducing the combined properties of the galaxy. The disagreement between 10% and 50% does not make the observation useless. It demonstrates how difficult metallicity measurements become under conditions that have few exact counterparts nearby. Most metallicity calibration methods are developed by studying galaxies whose physical conditions can be measured in much greater detail. JADES-GS-Z14-O has an unusually intense radiation field, low dust content, young stellar population, and extreme redshift. Applying familiar diagnostic relationships requires caution. The important result is not that one particular percentage has been permanently established. It is that multiple independent measurements continue to require non-negligible oxygen enrichment at an age below 300 million years. More recent observations have made the feedback side of the story equally interesting. A 2026 study using additional Webb spectroscopy reported unusually strong and spatially extended C3 emission. The carbon-emitting region appeared displaced by roughly 400 parsecs from the main stellar continuum. The authors interpreted this as possible evidence for enriched gas carried outward by an ongoing or earlier galactic outflow. Under that interpretation, the inferred mass outflow rate was about 160 solar masses per year, several times greater than the current star formation rate. The authors argued that strong outflows could regulate star formation even at this remarkably early period. They also found that moderate star formation efficiency combined with low dust attenuation may help explain the bright appearance of galaxies like JADES-GS-Z14-0. The result remains a recent interpretation rather than a settled measurement of the galaxy's full history, but it gives astronomers a concrete feedback mechanism to test. This is an important change in the discussion. The earliest reaction to surprisingly bright Webb galaxies sometimes focused on the possibility that star formation efficiency had to be dramatically increased. If outflows really are carrying large quantities of material away from JADES-GS-Z14-O, then the galaxy may not require absurdly efficient conversion of all available gas into stars. It could instead be bright because several effects work together. Moderately efficient star formation creates a strong young stellar population. Low dust attenuation allows more of the ultraviolet radiation to escape. Bursty activity means we preferentially observe the system during an unusually luminous phase. A stellar population weighted toward massive stars could add still more ultraviolet radiation and oxygen. Feedback then expels enough material to prevent the galaxy from growing without limit. That combination is less exotic than rewriting the basic laws of cosmology, but it still requires galaxy formation models to behave differently at early times. This distinction is worth keeping clear because phrases such as rewriting cosmic dawn can easily become stronger than the evidence. The discovery does not show that the Big Bang model is wrong. It does not show that the universe is older than measurements indicate. It does not show that standard gravity stopped working during the first few 100 million years. It does not require abandoning dark matter. The main pressure is currently on the astrophysics occurring inside growing dark matter halos. How gas cools, how efficiently stars form, what kinds of stars form, how dust develops, how strongly feedback operates, and how observable light relates to underlying mass. These are major questions, but they are different from replacing the entire cosmological framework. Dark matter simulations can create structures early enough to host galaxies. The difficulty lies in predicting how much light those structures should produce and how quickly their gas should become chemically enriched. That is precisely where observations like JADES-GS-Z14-0 are most useful. A model can no longer be judged only by whether it produces some galaxies by redshift 14. It has to produce galaxies with realistic brightness, size, star formation histories, metallicities, ionization states, gas fractions, dust content and abundance, it must also produce the correct number of them. This last point has become increasingly important because JADES-GS-Z14-0 is no longer alone at the distance frontier. In January 2026, astronomers announced the spectroscopic confirmation of MOM-Z14 at a redshift of 14.44. Its light shows the galaxy as it existed about 280 million years after the Big Bang, making it slightly earlier than JADES-GS-Z14-0 and moving the observational frontier closer to the first stars. NASA described MOM-Z14 as part of a growing population of unexpectedly bright early galaxies and reported that such systems were appearing far more frequently than many pre-Webb theoretical predictions had indicated. Records will continue to move. That is almost guaranteed. Webb has not surveyed the entire sky to the same depth, and its deepest programs examine tiny areas compared with the full celestial sphere. As more fields are observed and more candidates receive spectroscopy, other galaxies will probably be confirmed at redshifts beyond the current record. The scientific value of JADES-GS-Z14-0 does not depend on keeping a trophy for greatest distance. Its importance comes from the detail available. Astronomers have measured its ultraviolet light, size, Lyman break, oxygen emission at different wavelengths, hydrogen emission, carbon features, dust limits, and gas motions. ALMA and Webb are turning one faint object from the first 300 million years into something closer to a physical laboratory. This is a major change from the state of early galaxy astronomy before Webb. Hubble could identify candidate galaxies from very early periods, but obtaining detailed spectra was extraordinarily difficult. Researchers often had to infer properties from a few photometric measurements. Webb extended spectroscopy much farther into cosmic dawn. ALMA can then target far infrared lines shifted into millimeter wavelengths. The two facilities together allow astronomers to move beyond asking whether a galaxy exists. They can ask what it is made of. They can estimate how quickly it forms stars. They can study its ionized gas. They can search for dust. They can measure internal velocities. They can test whether gas is leaving. They can compare oxygen with carbon and eventually with additional elements. This changes the kind of theory that can be tested. A simulation that predicts the correct number of bright galaxies but gives them almost no metals would fail. A simulation that produces the right metallicity but requires far more dust than observations allow would also fail. One that matches brightness but cannot create strong outflows would face another problem. The data are becoming multidimensional, and that makes the models easier to challenge. Reionization is another area affected by the results. During the first billion years, ultraviolet radiation from early luminous sources gradually ionized the neutral hydrogen filling intergalactic space. Galaxies are thought to have supplied much of that radiation, although exactly which galaxies dominated remains under investigation. If bright galaxies were more common at redshifts above 10 than previously expected, they may have contributed more ionizing radiation at earlier times. JADES-GS-Z14-0 appears to produce ionizing photons efficiently. Its low dust content would help radiation escape from the immediate stellar environment, although neutral gas surrounding the galaxy can still absorb much of it. Outflows may create lower density channels through which ionizing photons escape more easily. The relationship between feedback and reionization is therefore complicated. Feedback can reduce star formation by removing gas, decreasing future photon production. At the same time, clearing gas from around young stars may allow a larger fraction of existing ionizing photons to reach intergalactic space. The same outflow could suppress one part of the process and enhance another. This is why models of cosmic dawn have to connect galactic structure with the large-scale evolution of the universe. One small star-forming region affects gas inside a galaxy. Thousands or millions of galaxies affect the ionization state of intergalactic hydrogen. Enough individual systems eventually change what the universe looks like on enormous scales. JADES-GS-Z 14-0 provides only one point in that larger process, but it tells us that intense stellar activity and substantial enrichment were already possible very early. The next step is statistical rather than spectacular. Astronomers need many more objects. A rare galaxy can teach us what is physically possible. A population tells us what was normal. Future Web surveys can identify fainter systems that are probably much more numerous than bright sources like JADES-GS-Z 14-0. ALMA can target oxygen, carbon and dust in selected objects. Larger samples can show whether metallicity rises smoothly with stellar mass, whether high O3 to C2 ratios are common, and whether outflows appear in most luminous early galaxies. Researchers also want direct evidence of truly metal-free stellar populations. JADES-GS-Z 14-. O is already too enriched to provide a clean example of the universe's first stars. Its oxygen tells us those first stages have passed. Finding population 3 signatures will probably require studying even earlier or less enriched regions, perhaps in small galaxies whose light is difficult to detect. Ironically, the discovery of early oxygen makes the search for the first stars both more urgent and more difficult. If chemical enrichment happened rapidly, the period during which a galaxy remained completely metal-free may have been brief. The first supernovae could alter local gas within only a few million years. A pristine galaxy might therefore be rare not because first stars were rare, but because their chemical fingerprints did not remain pristine for long. Cosmic dawn may have moved quickly. That is becoming one of the clearest messages from Webb and ALMA. Structures formed, stars ignited. Heavy elements appeared, gas was expelled and replaced. Some galaxies became bright enough for us to see across more than 13 billion years. The sequence that once occupied a broad theoretical interval is beginning to look crowded with activity. Scientists will adjust their models as the observations improve. Some apparent tensions will probably disappear when better measurements reduce uncertainties. Other problems may become stronger. New parameters will be tested. Assumptions about stellar populations, feedback and dust will change. That process does not weaken the science. It is the science. A useful model makes predictions before every detail is known. A new telescope checks those predictions in a region that was previously inaccessible. When reality does something unexpected, the model becomes more precise by having to explain it. JADES-GS-Z 14-0 has done exactly that. Its oxygen does not overturn our understanding of stellar nucleosynthesis. We know how stars can make oxygen. It does not require a new element or an unknown nuclear reaction. The difficulty lies in the speed, quantity, and environment. The universe had enough time to produce oxygen, but this particular galaxy appears to have used that time remarkably efficiently. And once that fact is accepted, the subject becomes much less distant from ordinary experience than its redshift might suggest. Oxygen is not only a spectral line at 223.5 GHz. It is an element present throughout the world around us. The same atomic identity that ALMA recognized in radiation from a galaxy seen less than 300 million years after the Big Bang is represented by the oxygen in rocks, water, plants, animals and the air. That does not mean the oxygen detected in JADES-GS-Z 14-0 travelled here and ended up in your lungs. That galaxy is far too distant, and its material belongs to an entirely different region of the universe. The connection is not a physical delivery route. The connection is the process. Before stars existed, the universe had almost no oxygen. Hydrogen and helium dominated the ordinary matter left after the Big Bang. Gravity gathered that material. Stars formed. Inside sufficiently massive stars, helium fusion produced carbon, and carbon captured helium nuclei to make oxygen. Those stars later returned part of the oxygen to space. The next generation formed from more complicated material than the previous one. The process repeated. Galaxies gradually became chemically richer. Our own galaxy participated in the same broad history. The Milky Way did not exist in its present form during the time represented by JAD-ES-GS-Z14-0. Its history developed later through the growth and merger of earlier structures. Generations of stars formed, evolved, and enriched interstellar gas over billions of years. Some of those stars produced oxygen. Others contributed carbon, nitrogen, silicon, magnesium, iron, and many additional elements. When the cloud that eventually formed the Sun collapsed about 4.6 billion years ago, it was already chemically enriched. The Sun therefore did not form from primordial hydrogen and helium. It formed from gas containing the products of many earlier stars. The same was true of the material that became the planets. Oxygen was one of the most abundant, heavier elements in that cloud. Much of it combined with silicon, magnesium, iron, and other elements to form minerals. Some combined with hydrogen to form water. Earth incorporated large quantities of oxygen from the beginning of its formation, although most of it was chemically bound rather than floating freely in an atmosphere that humans could breathe. This distinction is easy to miss. The element oxygen and the molecule O2 are not the same thing. ALMA detected radiation from doubly ionized oxygen atoms in JADES-GS-Z14-0. The oxygen around us appears in many forms. Water contains one oxygen atom joined to two hydrogen atoms. Carbon dioxide contains carbon joined to oxygen. Most rocks contain oxygen bound into minerals. The atmosphere contains molecular oxygen, O2, in which two oxygen atoms are bound together. The oxygen atoms in all of those substances share the same defining feature. Each nucleus contains 8 protons. The atmosphere did not begin with its present abundance of O2. Early Earth contained plenty of the element oxygen in rocks, water, and other compounds. But free molecular oxygen was initially scarce. Living organisms later changed that. Oxygenic photosynthesis uses light energy to take electrons from water during the process of building chemical energy. Molecular oxygen is released as a byproduct. Over enormous periods, biological oxygen production altered the atmosphere and oceans. The Great Oxidation Event, beginning roughly 2.4 billion years ago, marked a major rise in atmospheric oxygen, although the history involved several stages rather than one sudden morning, when every creature noticed that breathing had improved. The oxygen atoms released by photosynthesis were not newly created in the nuclear sense. Biology rearranged existing atoms. Plants, algae, and cyanobacteria cannot manufacture oxygen nuclei from hydrogen. That requires nuclear reactions at temperatures and pressures found inside stars. Photosynthesis changes chemical bonds. Stars change atomic nuclei. The difference is important because it gives the oxygen in every breath two very different histories. Its nuclear history is stellar. Its atmospheric history is strongly biological. The atom had to exist before life could place large quantities of O2 into Earth's atmosphere. Every breath, therefore, depends on processes operating at radically different scales. Massive stars created the element. Galactic chemical evolution distributed it. The solar system incorporated it. Earth's geology stored it in water and minerals. Life eventually released part of it into the atmosphere. Your lungs then exchange it with your bloodstream through structures only fractions of a millimeter thick. None of this requires imagining that individual oxygen atoms have remained in one form through the entire sequence. They move constantly. An oxygen atom can be part of water, enter a plant, leave as molecular oxygen, enter an animal, become part of carbon dioxide, dissolve in an ocean, and later participate in another chemical reaction. What remains unchanged through ordinary chemistry is the nucleus. 8 protons still identify oxygen. That is what makes the ALMA observation feel surprisingly familiar once the enormous distance is removed from the explanation. An ionized oxygen atom in JADES-GS-Z14-O and an oxygen atom in a glass of water obey the same atomic physics. Their electrons can occupy the same allowed energy states. Their spectral transitions follow the same rules. Astronomers depend on that consistency. If oxygen behaved differently in a galaxy 13 billion light-years into our past, laboratory spectroscopy would not provide a reliable identification. Instead, the laws measured here allow us to recognize an element there. The 88 micrometer O3 line is a direct consequence of the internal energy structure of the ion. Cosmic expansion stretches the wavelength, but it does not erase the information. ALMA measures the shifted radiation. Astronomers compare it with the known transition. The element identifies itself through physics that operates the same way across an extraordinary range of time and distance. This consistency is part of what makes observational cosmology possible. We cannot travel to JADES-GS-Z14-0. We cannot collect a gas sample. We cannot send a probe and wait for laboratory results. Even a message travelling at the speed of light would require billions of years to make the trip. Instead, the experiment comes to us. Photons leave the galaxy. Space expands while they travel. Some reach Earth. An array of antennas on a dry plateau measures them. The resulting data contain enough information to identify oxygen and determine the galaxy's redshift. That entire result began with atomic events and gas surrounding stars that lived when the universe was a small fraction of its current age. Those stars had no knowledge of the Milky Way because the Milky Way had not yet developed into the galaxy we know. The Sun did not exist. Earth did not exist. There were no people to name oxygen. There were no telescopes. The photons began travelling anyway. For most of their journey, our solar system was absent. The Milky Way evolved while the light crossed intergalactic space. Generations of stars formed and died here. The Sun appeared. Planets assembled around it. Earth cooled. Life developed. The atmosphere changed. Complex organisms evolved. Humans eventually learned to separate light into spectra and identify chemical elements. Then humans built radio telescopes. Eventually, they placed 66 antennas on a high plateau in Chile and taught computers to combine their signals with extreme precision. The old photons finally arrived. There is nothing mystical required in that sequence. It is simply what a long light travel time means. The observation allows 2 histories to meet at the instrument. One is the history of the distant galaxy. The other is the history of the observers who eventually became capable of detecting it. ALMA's result is especially satisfying because the signal is so ordinary in form. There was no explosion visible across the sky. No nearby star suddenly changed colour. The evidence was a line in a spectrum. Most people could look at the graph without immediately recognising anything important. Astronomers knew that the line had a rest wavelength. They knew the predicted redshift. They knew how expansion should shift the frequency. They knew how ionized oxygen behaves. A small feature became a measurement of chemical development near the beginning of galaxy formation. That is often how astronomy works. A great deal of significance can be packed into a feature that would be easy to overlook. A dip in brightness reveals a planet. A tiny shift in spectral lines reveals motion. A slight distortion in the shape of a galaxy reveals gravitational lensing. A weak millimeter signal reveals oxygen created more than 13 billion years ago. Large scientific conclusions do not always arrive looking large. The story began tonight with an observatory in the Atacama Desert, because ALMA gave the oxygen a measurable signature. From there, the trail moved backward. We passed through the galaxy's ionized gas and into earlier generations of stars. We followed helium becoming carbon and carbon becoming oxygen. We looked at massive stars that lived only a few million years. We considered supernovae that released newly formed material into surrounding gas. We returned to the young galaxy and asked how it could repeat those processes quickly enough to become enriched before the universe reached 300 million years of age. Then the question widened. If JADES-GS-Z14-O developed this quickly, perhaps other early galaxies did too. Webb has already shown that surprisingly luminous systems are not limited to one object. MOM-Z14 has now moved the confirmed distance frontier a little earlier, to a time around 280 million years after the Big Bang. It joins a population that continues to make the first few hundred million years look more active than many astronomers expected before Webb. Future observations may move the frontier earlier again. Another galaxy will eventually receive attention for being the most distant. Then another may take its place. Distance records are temporary. The chemical question will remain. How quickly can a galaxy stop being primordial? How soon after the first stars appear can oxygen become common enough to detect? How efficiently can a tiny early system retain the products of its own supernovae? How much material escapes? How much returns? How much new gas arrives? Which stellar masses dominate the enrichment? Those questions can now be tested with observations rather than left almost entirely to simulations. That is one of the most important consequences of the discovery. Cosmic dawn has become an experimental subject. Not experimental in the sense that astronomers can alter a galaxy and repeat the conditions. They cannot turn star formation off, reset the universe to 290 million years old, and try again with slightly less dust. But they can collect enough galaxies to compare different natural outcomes. One may be bright and metal-rich. Another may be faint and primitive. A third may contain strong oxygen but little carbon. A fourth may show large amounts of dust. The population becomes a set of tests. ALMA can provide the millimeter measurements. Webb can supply infrared spectra. Future facilities will add still more sensitivity and resolution. The models will become less free to choose whichever early history seems convenient. They will have to match what the galaxies actually did. JADES-GS-Z14-O may eventually become less unusual as the sample grows. That would not make the discovery less important. The first object that reveals a common phenomenon often seems extraordinary only because no one had been able to see the rest of the population. Hot Jupiters once seemed bizarre. Fast radio bursts were once isolated mysteries. Very distant luminous galaxies may follow the same pattern. The alternative is equally interesting. If larger surveys show that JADES-GS-Z14-0 is genuinely rare, astronomers will need to explain what made its particular environment so effective. Perhaps it occupied an unusually massive halo. Perhaps it formed in an exceptionally dense region. Perhaps its stellar population differed from the average. Perhaps inflowing gas and feedback happened to balance in a favourable way. Rare objects test the limits of models just as effectively as common ones test their averages. For now, the evidence supports a simpler statement. The first galaxies could evolve quickly, faster, in at least some cases, than many earlier expectations suggested. Within a few 100 million years, gravity had already built environments where stars could form repeatedly. Nuclear fusion had produced oxygen. Supernovae and stellar winds had released heavy elements. Ionized gas was shining strongly enough for ALMA to detect it after an enormous journey. That is enough to make the early universe look busier than the old simplified picture. There was no long empty pause followed by a slow introduction of chemistry. Once stars appeared, some regions changed rapidly. The universe began with a short list of elements. Stars expanded the list. Galaxies kept the record of those changes in their gas. Much later, planets inherited the results. Our own surroundings are one outcome of the same general process carried much farther forward. The oxygen in the room around you belongs to a mature stage of cosmic chemical evolution. Earth contains far more chemical complexity than JADES-GS-Z 14-0 could have possessed at the time we observe it. There are rocks containing combinations of elements that required many earlier stellar generations. There is liquid water at the surface. There is an atmosphere maintained partly by living organisms. There are cells using oxygen to release energy from food. None of that existed in the young galaxy ALMA measured. What did exist was one necessary ingredient. The element itself had already appeared. That makes the discovery a useful marker in the history between the simple chemistry after the Big Bang and the complex chemistry of later planets. Oxygen is particularly important because it is one of the most abundant heavy elements produced by massive stars. It becomes a major component of rocky planets. It combines readily with other elements. It is common in silicate minerals. It forms water with hydrogen. Its presence does not imply life, but a universe without oxygen would lack much of the chemistry we take for granted. ALMA did not find evidence for oceans or biological activity in JADES-GS-Z14-0. There is no reason to interpret the line that way. It found evidence that the raw chemical inventory of the universe was already expanding quickly. That distinction keeps the result both accurate and impressive. There is no need to add aliens to make a redshift 14 oxygen detection interesting. The stars have already done enough. If you happen to notice you're breathing while listening, there is no need to change it or count it. The oxygen involved is doing something very different from the oxygen ALMA observed. Oxygen molecules enter the lungs, cross into the blood, and participate in cellular respiration. The atoms remain ordinary oxygen atoms while chemistry moves them between molecules. The nucleus in each one represents a process that chemistry cannot perform. Some earlier star had to make it. We cannot identify which star produced any particular oxygen atom in the room. The solar system inherited material that had been mixed through the interstellar medium. Many stellar sources probably contributed. Massive stars and their explosions supplied a large fraction of the oxygen. That uncertainty is normal. Cosmic chemical history is a shared inheritance, rather than a labelled collection. There is no tiny certificate attached to an oxygen atom saying which supernova produced it. Astronomers reconstruct the history statistically from elemental abundances, stellar models, meteorites, spectra, and the structure of the galaxy. The same method is now being extended much farther back. Instead of using only old stars in the Milky Way as fossils of earlier enrichment, astronomers can observe young galaxies directly during the period when the enrichment was occurring. JADES-GS-Z 14-0 is not a fossil. We see it in operation. The oxygen line records gas already enriched while young stars continue to ionize it. Possible carbon-rich outflows show material being moved around. Hydrogen emission measures current star formation. Dust limits constrain another product of stellar evolution. Each observation adds one piece of the active system. That may be the most useful way to think about cosmic dawn now. It was not simply the time when the first lights turned on. It was the beginning of feedback loops. Stars changed the gas that made later stars. Supernovae altered cooling. Metals changed fragmentation. Radiation changed ionization. Outflows changed gas supply. Each generation modified the conditions inherited by the next. Once that cycle began, galaxy evolution could accelerate. JADES-GS-Z 14-0 appears to have entered the cycle early and moved through it quickly. ALMA happened to catch one chemical consequence. The observation will be refined. Metallicity estimates will change. Models will improve. Other galaxies will provide comparisons. Some details described today may look different after another decade of observations. The central measurement is much more secure. A strong O3 line was detected from JADES-GS-Z 14-0 at redshift 14.1793. Oxygen existed in an actively star-forming galaxy roughly 290 million years after the Big Bang. That fact now belongs in any serious account of how rapidly early galaxies could evolve. And after following that signal from a Chilean plateau back through 13 billion years of cosmic history, we can return to a much smaller scale. Perhaps the room is quiet now. Perhaps the screen is the brightest object nearby. Maybe you are listening from a city where the sky contains only a few visible stars, or from somewhere dark enough to see the Milky Way clearly. Wherever you are, the oxygen around you is not evidence that our region of the universe was special from the beginning. It is evidence that stars have been doing this work for a very long time. The early universe started simply. It did not stay simple. JADES-GS-Z14-O shows how quickly that change could begin. If this journey through the first oxygen-rich galaxies has been useful, you can leave a like or subscribe to Science for Sleep. It helps other listeners find these longer, quieter explorations, and it lets us keep looking at the parts of science that become more interesting when there is enough time to explain what the measurements actually mean. You can also leave a comment with where you are listening from. It seems appropriate after spending so long discussing a signal that crossed most of the observable history of the universe. ALMA received it from northern Chile. Webb received other parts of the galaxy's light from its orbit around the Sun. Researchers in many countries analysed the measurements, and now the result can be heard almost anywhere on Earth, usually through a device containing elements that were themselves produced by earlier generations of stars. The comparison is not necessary for the science, but it is a useful reminder of scale. The universe was already manufacturing oxygen long before there was an Earth on which anyone could wonder where oxygen came from. The first massive stars did not produce it for us. They followed nuclear physics. Later stars did the same. Billions of years of chemical evolution eventually created environments where rocky planets and complicated molecules became possible. On one of those planets, life altered the atmosphere. Much later, one species learned enough spectroscopy to recognize oxygen in a galaxy from the first few 100 million years. That is where the story stands now, not with every question answered, not with a completely rewritten model of galaxy formation, with a better constraint. Galaxies could become bright and chemically developed very early. Some of them formed stars efficiently enough to create measurable oxygen within an unexpectedly short interval. Feedback was already operating. Outflows may already have been carrying enriched gas away. The earliest galaxies were not simple piles of hydrogen waiting patiently for the universe to become interesting. They were active physical systems. More observations will tell us how common that activity was. Until then, JADES-GS-Z14-0 remains one of the clearest examples we have. A faint galaxy in an exceptionally deep field. A small rise in an ALMA spectrum, an oxygen transition stretched from far infrared radiation into millimeter wavelengths, a redshift measured to remarkable precision, and a piece of evidence that the chemical universe began developing earlier and faster than many astronomers expected. So, if your thoughts have become a little slower by now, there is nothing more you need to calculate. No redshift needs solving. No stellar mass needs estimating. The antennas can remain in the Atacama Desert. The old photons can continue arriving, and astronomers can keep working through the questions they bring with them. For tonight, the important part is simple. The universe began mostly with hydrogen and helium. Stars made oxygen. Some galaxies began that work very early. ALMA found the evidence, and much later, after countless generations of stars and an entirely separate history here in the Milky Way, oxygen became part of the planet beneath us, the water around us, and the air moving quietly through our lungs. Sleep well, wherever you are listening from, and whatever time it happens to be there.